Picture, for a moment, a world not of serene oceans and gentle breezes, but one where the very sky is a weapon. Imagine standing on a distant exoplanet, watching as clouds of molten silicate glass are whipped by supersonic winds, scouring the landscape with a horizontal, razor-sharp rain. This isn't a scene from the most ambitious science fiction film. This is a real, documented environment out there in the vast darkness, a place where the laws of physics as we know them are pushed to terrifying and beautiful extremes. It's a stark reminder that the universe is not just a collection of pretty stars, but a gallery of the most hostile, bizarre, and profoundly strange places imaginable. We often gaze up at the night sky and see a tapestry of peaceful, twinkling lights, but behind that serene facade lies a reality of unimaginable violence and wonder, a cosmos that operates on a scale of power and strangeness that can dwarf our wildest fantasies. This journey we're beginning today is an invitation to step beyond that familiar view, to pull back the curtain and confront the true, raw nature of the cosmos in all its terrifying glory. We are about to embark on a voyage to the universe's most extreme environments, places that defy logic and challenge our very understanding of what is possible. From the very first fact to the last, we will be exploring realms where gravity is so intense it crushes atoms into a super-dense soup, where temperatures soar to millions of degrees or plunge to near absolute zero, and where the very fabric of space and time is warped into knots by forces beyond our comprehension. This is not a casual tour, it is a deep dive into the cutting edge of astronomical discovery, a collection of 50 incredible facts that reveal the universe not as a peaceful void, but as a dynamic, chaotic, and breathtakingly active arena. Each fact is a doorway into a new understanding, a piece of a puzzle that shows us just how small, and yet how incredibly curious we truly are. So settle in and open your mind, because we are about to travel to the crushing depths of neutron stars, soar through the superheated atmospheres of hellish exoplanets, and peer into the abyssal hearts of black holes. This is a journey designed to inspire awe and thrilling discovery, to fill you with a sense of wonder at the sheer audacity of the cosmos and the relentless human drive to understand it. Let's begin our countdown of 50 facts about the universe's most extreme environments, starting with a place that redefines the word hostile. Our first stop on this cosmic tour takes us 40 light-years from Earth to a world orbiting a dim red star known to astronomers as Gliese 1214b. This isn't a planet of rock or gas as we typically picture them. It is a vast global ocean. Unlike Earth's distinct continents and seas, this entire world is one single, uninterrupted body of water, a true water world. But before you imagine a paradise of gentle waves and tropical shores, you must understand the true nature of this alien sea. The planet orbits so close to its star that the surface temperature soars to hundreds of degrees Fahrenheit. This means the ocean isn't a placid, blue expanse, it is perpetually, violently boiling. Yet, because of the immense atmospheric pressures hundreds of times greater than what we experience at sea level, the water cannot simply turn to steam and escape into space. Instead, it's trapped in a perpetual, churning state, a superheated liquid beneath a thick, steamy atmosphere that is more like a global pressure cooker than a planet. This combination of extreme heat and crushing pressure gives rise to one of the most fascinating aspects of this environment, the creation of exotic states of water. On Earth, we're familiar with solid ice, liquid water, and gaseous vapor. But under the staggering pressures found on Gliese 1214b, water can be forced into strange, high-density forms that are both liquid and solid, or even a supercritical fluid that has properties of both a liquid and a gas. Scientists theorize that deep below the boiling surface, the pressure could be so intense that it forms a type of ice, but not ice as we know it. This wouldn't be cold, crystalline ice, but rather a hot, dense, solid form of water known as Ice 7, or other exotic ices that can only exist under such tremendous forces. This single planet, therefore, presents us with a layered world of extremes, a seething, boiling upper ocean, a deep abyss of bizarre, hot ice, and an entire global ecosystem of water existing in states that are, for us, purely theoretical. It is a stark and powerful demonstration that even a substance as fundamental as water can behave in ways that completely defy our everyday experience, sculpting environments in the cosmos that are as bewildering as they are magnificent. Leaving the churning, superheated oceans of Gliese 1214b behind, we journey next to a world that seems ripped from the pages of an interstellar treasure hunter's log. Imagine a planet where the very ground beneath your feet, if you could stand on it, might be composed of the universe's most sought-after gem. 40 light-years away in the constellation of Cancer, orbiting the star 55 Cancri, lies a super-Earth known as 55 Cancri e, a world so rich in carbon that astronomers believe a significant portion of its interior could be a solid, crystalline diamond. This isn't a small vein or a hidden deposit. We are talking about a core that could be diamond on a planetary scale, a glittering geological heart forged in the most extreme conditions imaginable. The story of how such a world comes to be begins with its star. Our own sun is rich in oxygen and silicon, which is why the Earth and its rocky siblings are known as silicate planets, built from mountains of rock and metals. But 55 Cancri is a carbon-rich star, meaning the cloud of dust and gas from which its planets formed was teeming with carbon atoms. In this cosmic crucible, the planet 55 Cancri coalesced, accumulating vast quantities of carbon instead of the oxygen and silicon that dominate our own solar system. Under the incredible heat and pressure deep within a forming planet, carbon undergoes a spectacular transformation. Just as coal is compressed into diamond deep within the Earth over eons, the carbon on this super-Earth was subjected to far more intense forces. With a mass nearly 8 times that of our own world and a scorching surface temperature hot enough to melt most metals, the internal pressures are staggering. These conditions are perfect for forcing carbon atoms to bond in the rigid, tetrahedral lattice structure that defines a diamond. Scientists estimate that up to a third of the planet's mass, a mass 3 times the size of Earth, could be this precious crystalline material. The surface of this world is just as extreme as its interior. It orbits so close to its parent star that a year passes in just 18 hours, locking one side in perpetual, blistering daylight and the other in eternal night. This proximity has likely created a global lava ocean on its day side, a seething, incandescent sea of molten rock. So the picture we have is almost paradoxical. A planet with a surface of unimaginable heat and violence, concealing a heart of cold, perfect crystal. This diamond core hypothesis fundamentally changes our perspective on what a planet can be. It tells us that the building blocks available around different stars can lead to planetary compositions that are utterly alien to our own experience. We have gas giants, ice giants, and rocky worlds in our solar system, but the universe also contains carbon planets, potential diamond worlds, and who knows what other mineralogical marvels. The existence of 55 Cancri e suggests a cosmos far more mineralogically diverse and extravagant than we ever dreamed, a place where the very stuff of stars can be forged into treasures of almost mythical proportions. While we can't mine it, the journey is impossibly long, and the surface conditions are utterly lethal. The value of this world isn't in its potential for jewelry. Its true worth is as a natural laboratory, a key to understanding the incredible variety of planetary systems that fill the galaxy, proving that the universe is not just a place of destructive forces, but also one of astonishing and literal creation. From the glittering, diamond-filled depths of a distant super-Earth, we now turn our gaze to a world much closer to home, a planet that serves as a stark and sobering warning about how a climate can spiral completely out of control. Welcome to Venus, our so-called sister planet, a title that could not be more misleading. While Venus is similar to Earth in size and composition, its environment is the most hellish in our entire solar system, a true planetary inferno where the very concept of a hospitable world has been utterly erased. The journey to the surface of Venus is a descent into a progressively more terrifying reality. As a spacecraft plunges through the upper atmosphere, it first encounters those famous, beautiful clouds that reflect so much sunlight, making Venus the brightest object in our night sky after the moon. But these are not clouds of water vapor. They are thick, choking clouds of sulfuric acid, a corrosive mist that rains down droplets of battery acid. This acid rain, however, never reaches the ground. The intense heat at lower altitudes causes it to evaporate before it can hit the surface, creating a perpetual, vicious cycle of condensation and evaporation in the middle atmosphere. The true horror, however, is revealed as you go deeper. The atmosphere of Venus is not just a layer of gas, it is an immense, crushing ocean. The pressure at the surface is 92 times the pressure we experience at sea level on Earth. To put that in perspective, it is the equivalent of being nearly 1 kilometer deep in the ocean. The few Soviet Venera landers that successfully reached the surface didn't just have to withstand incredible heat. They had to be constructed like submarines with massive, pressure-resistant hulls designed to survive for mere minutes before being crushed and melted by the planet's fury. This overwhelming pressure is a direct result of the atmosphere's composition, which is almost entirely carbon dioxide. This leads us to the engine of this hellscape, the runaway greenhouse effect. On Earth, we have a delicate balance where certain gases, like carbon dioxide, trap just enough of the sun's heat to keep our planet warm. On Venus, that process has spiraled into a catastrophic feedback loop. Billions of years ago, Venus may have had oceans, but as the sun grew brighter, those oceans began to evaporate. Water vapor is itself a potent greenhouse gas which trapped more heat, causing more evaporation. This continued until the oceans were gone and all the water had been lost to space. The carbon dioxide that was once locked away in rocks was then baked out into the atmosphere, creating the thick, suffocating blanket we see today. This blanket traps solar energy with terrifying efficiency, driving surface temperatures to an average of 867 degrees Fahrenheit, 464 degrees Celsius. That is hot enough to melt lead, to soften zinc, and to ensure that no complex organic molecule, the building block of life as we know it, could possibly survive. The surface itself is a scorched volcanic plain, illuminated by a dim, orange glow through the thick clouds, with a landscape of cracked rock under a sky that is anything but inviting. The terrifying lesson of Venus is that it represents a possible end state for a planet that was once perhaps not so different from our own. It is a permanent reminder of the awesome power of planetary climate systems and the delicate equilibrium that makes our own blue marble so rare and so precious. This isn't just a hostile environment, it is a monument to a climate catastrophe on a global, permanent scale, showing us with brutal clarity what happens when a greenhouse effect is allowed to run away with itself, transforming a sister world into the solar system's most intense and unforgiving cauldron. After witnessing the scorching, static fury of Venus, we now travel outward to a world of pure, dynamic chaos, a place where stability is an alien concept and storms are measured on a planetary scale. Our next destination requires us to look not for solid ground, but to confront a fluid giant, Jupiter. This colossal planet, a vast sphere of swirling hydrogen and helium, is a study in atmospheric violence, and its most famous feature is a storm so immense it could swallow our entire world whole. This is the Great Red Spot, an anticyclonic tempest that has been churning in Jupiter's southern hemisphere for centuries, a furious crimson eye gazing out from the clouds. To truly grasp its scale, you must picture Earth with all its continents and oceans, and then realize that this single storm is over 10,000 miles across, large enough to fit our planet inside it with room to spare. It has been observed continuously by astronomers since the 1600s, meaning this hurricane has been raging for at least 400 years, and geological evidence suggests it may be far older. The mechanics behind such an enduring cataclysm are fundamentally different from the storms we experience on Earth. Our hurricanes are powered by warm ocean water and are eventually torn apart when they move over land or into cooler waters. But Jupiter is a gas giant with no solid surface to disrupt the flow of its atmosphere. The Great Red Spot is essentially a gigantic, self-sustaining vortex of gas, an island of high pressure trapped between two powerful, opposing jet streams that race around the planet in opposite directions. This stable positioning allows it to act like a massive atmospheric wheel, constantly drawing in material from its surroundings and spinning it with unimaginable force. The wind speeds at the outer edges of this storm are a terrifying testament to its power, routinely exceeding 268 miles per hour, speeds that make the most powerful Category 5 hurricanes on Earth seem like gentle breezes. The energy required to sustain such velocities for centuries is almost beyond comprehension, and it comes from two primary sources: the intense heat welling up from Jupiter's molten interior and the planet's incredibly rapid rotation. A day on Jupiter lasts only about 10 hours, and this fast spin whips its thick atmosphere into a complex tapestry of belts and zones, creating the sheer forces that birth and maintain these colossal vortices. But what of its striking color, that deep brick red hue that gives the spot its name? The prevailing theory suggests that the storm acts like a colossal elevator, dredging up material from deep within Jupiter's atmosphere. As these chemical compounds, likely phosphorus or sulfur-containing molecules, are lifted high into the upper cloud decks, they are exposed to the sun's powerful ultraviolet radiation, which triggers a chemical reaction that turns them a reddish color. So the Great Red Spot is not just a vast, empty swirl of wind. It is a continuous, violent geyser of chemistry, painting itself with the very gases it churns from the abyss below. While it has been shrinking slowly over the past century of observations, it remains the largest and most powerful storm system in our solar system, a permanent monument to the chaotic and energetic forces that govern the giant planets. It teaches us that weather is not merely a surface phenomenon, but a fundamental expression of a planet's entire energy budget, and on a world like Jupiter, that expression takes the form of an eternal, planet-eating maelstrom. Venturing outward from Jupiter's churning storms, we find an entirely different kind of world, one that feels less like a planet and more like a frozen echo of our own. Orbiting the majestic, ringed planet Saturn is Titan, a moon so large it challenges the very definition of a moon. As our spacecraft descends through its atmosphere, we don't see a crisp, starry blackness, but instead are enveloped by an impenetrable orange fog. This thick, hazy shroud is a photochemical smog created as sunlight breaks apart methane and nitrogen molecules high in the atmosphere, allowing them to recombine into complex organic compounds that drift slowly down to the surface. This haze obscures the view from orbit, hiding a landscape that remained one of the solar system's greatest mysteries until the Cassini-Huygens mission pierced the veil in 2005. What it revealed was nothing short of revolutionary. Titan is the only other place in our solar system with stable liquid bodies on its surface, but this is not a second Earth with watery oceans. On this frigid world where surface temperatures plummet to -290 degrees Fahrenheit, water is harder than granite, acting as the bedrock of the entire landscape. Instead, the role of water is played by liquid methane and ethane. These hydrocarbons, which are gases on our warm Earth, exist as liquids in Titan's deep freeze, creating a complete and active hydrologic cycle that eerily mirrors our own. Imagine standing on the shores of a Titanian sea. The ground beneath your feet is not soil or sand, but a mixture of water, ice, and solid, tar-like organic compounds. Before you stretches a vast, dark, and remarkably smooth body of liquid, not water, but liquid methane. The waves on this sea would be sluggish and slow-moving due to the liquid's low density and the moon's low gravity, and the rain that falls from the orange sky above is not a gentle shower, but a chilling drizzle of liquefied natural gas. These are not merely small puddles. Titan hosts enormous lakes and seas, with the largest Kraken Mare being larger than North America's Great Lakes. This means we are looking at a landscape with river valleys carved by methane rainfall, with delta formations where rivers have deposited sediments, and with shorelines that are shaped by tides, not from Titan itself, but from the gravitational pull of its parent planet, Saturn. The presence of this active hydrocarbon cycle makes Titan a prime target in the search for the building blocks of life. The complex chemistry happening in its atmosphere and on its surface is a kind of frozen in-time snapshot of the probiotic conditions that may have existed on the early Earth before life ever emerged. It is a natural laboratory for studying the steps that can lead from simple organic molecules to more complex ones, all taking place in an environment drenched in the very chemicals that are fundamental to life as we know it. So, while Titan's lakes are not swimming pools, they are pools of possibility, holding secrets not just about the geology of an alien world, but about the very chemical pathways that might lead across the cosmos to life itself. But our tour of Saturn's extraordinary moons doesn't end with the hydrocarbon lakes of Titan. We must now turn our attention to a much smaller, seemingly unremarkable world that hides one of the solar system's most profound secrets. This is Enceladus, a brilliant white sphere of ice barely 300 miles across, looking like a perfect frozen marble against the blackness of space. For decades, astronomers considered it just another inert, icy moon, a geologically dead relic from the solar system's early days. That all changed in 2005 when the Cassini spacecraft made a breathtaking discovery. As it flew past this tiny moon, its instruments detected something impossible. Giant, shimmering plumes of water vapor and microscopic ice crystals erupting hundreds of miles into space from its south polar region. Enceladus wasn't a frozen corpse, it was alive, actively spewing its own internal contents out into the void in a spectacular, ongoing display. These are not volcanoes of molten rock, but something far more exotic, cryovolcanoes or cold volcanoes. Instead of erupting with scorching lava, they blast forth water, ammonia, methane, and other volatile substances that would normally be frozen solid. The energy required to power such a dramatic phenomenon on a moon so small was a monumental puzzle. The answer lies in the gravitational relationship between Enceladus and its colossal parent, Saturn. Enceladus does not orbit in a perfect circle. Its path is slightly elliptical. This means that as it travels around Saturn, the planet's immense gravitational pull tugs on it with varying intensity, constantly flexing and squeezing the moon's interior. This process, known as tidal heating, generates enough friction and warmth to keep a vast reservoir of water liquid beneath the icy crust. We now know that Enceladus harbors a global subsurface ocean, a salty sea trapped between its rocky core and its outer shell of ice. The plumes we see are essentially geysers blasting directly from this hidden ocean into space through massive cracks in the ice, known as the tiger stripes for their distinctive appearance near the South Pole. This realization alone was revolutionary, but Cassini's findings went even further. When the spacecraft flew directly through these plumes, its mass spectrometer analyzed their composition and found that they were not just simple water. They contained a surprising mix of sodium chloride, common table salt, as well as silica nanoparticles and a variety of simple organic molecules like methane, carbon dioxide, and propane. The presence of the silica nanoparticles in particular was a crucial clue. Scientists determined that these tiny grains could only form in water that is in contact with rock at temperatures of at least 194 degrees Fahrenheit. This points to the existence of hydrothermal vents on the seafloor of Enceladus, where superheated water, rich in minerals, is jetting up from the rocky core into the cold ocean above. This is a landmark discovery. On Earth, deep-sea hydrothermal vents are teeming with life, hosting entire ecosystems that thrive in total darkness, independent of the sun's energy. The chemicals and heat from these vents provide all the nourishment needed for complex microbial communities and strange animals like tube worms to flourish. The conditions on the seafloor of Enceladus appear to be strikingly similar. It possesses the three fundamental ingredients for life as we know it: liquid water, a source of chemical energy, and a rich soup of organic compounds. This tiny, icy moon has rocketed to the top of the list of the most promising places in our solar system to search for extraterrestrial life. The plumes offer an incredible gift to scientists. They provide a free sample of this hidden ocean, delivered directly to any passing spacecraft. We don't need to land and drill through miles of ice. We can simply fly through the plume and analyze what's coming out. The implications are staggering. It suggests that the processes that gave rise to life on our own planet may not be unique, but could be occurring right now in the dark, warm abyss of a small moon orbiting a ringed giant, forever changing our understanding of where life can take hold in the cosmos. But if you think the visible storms of Jupiter are fierce, wait until you encounter the invisible fury that surrounds it. We must now venture into a domain of pure energy, into the heart of the most powerful particle accelerator in our solar system, the radiation belts of Jupiter. This is not a place you can see with a telescope. It is a tortured region of space, shaped and dominated by the gas giant's overwhelming magnetic field. To understand the sheer scale of this magnetic force, picture the largest magnet you can possibly imagine. Now multiply that by a factor of almost 20,000. Jupiter's magnetic field is a behemoth, so vast that its magnetosphere, the bubble of space it controls, would appear larger than the full moon in our sky if our eyes could see it in the night. It is generated by a dynamo deep within the planet, where immense pressures crush hydrogen into a bizarre metallic form that can conduct electricity. This layer of liquid metallic hydrogen, spinning at ferocious speeds, creates a magnetic field that is both a shield and a prison. As the solar wind, a constant stream of charged particles from the sun, washes over Jupiter, this colossal magnetic field captures and seizes these particles, along with others spewed forth by its volcanic moon, Io. It then funnels them into two gigantic, donut-shaped zones that encircle the planet's equator, known as the radiation belts. Within these belts, electrons, protons, and heavier ions are whipped to nearly the speed of light, trapped in a relentless, spiraling dance between the planet's magnetic poles. The energy density here is unmatched anywhere else in our solar system, making the Van Allen belts around Earth seem like a gentle, background hum in comparison. A spacecraft passing through the most intense regions of Jupiter's radiation belts would receive a dose of radiation millions of times more powerful than a lethal dose for a human. This invisible hailstorm of high-energy particles is an existential threat to both electronics and life. It can fry computer circuits, corrupt memory, degrade solar panels, and penetrate shielding to alter the very DNA of any living organism on board. This is the primary reason why the Juno spacecraft, which is currently studying Jupiter, was built with a unique armored vault. Its most sensitive instruments are housed inside a 1 centimeter thick titanium shield, a high-tech suit of armor designed to withstand the relentless bombardment. And even with this protection, Juno follows a highly elliptical orbit that carefully avoids the most intense regions of the belts, diving in for close observations before retreating to a safer distance. These belts are not static. They are a dynamic and seething ocean of energy, pulsing with the planet's rotation and flaring with activity from its moons. The most significant contributor to this hellish environment is Io, the most volcanically active body in the solar system. Its constant eruptions spew vast amounts of sulfur and oxygen ions into space, which are immediately ionized and captured by Jupiter's magnetic grip. This continuous injection of fresh fuel constantly re-energizes the belts, making them even more potent and deadly. So, while Jupiter presents a gorgeous, swirling face to our telescopes, it is cloaked in an invisible, lethal shroud of its own making, a stark reminder that the beauty of the cosmos is often guarded by forces of unimaginable power. Yet this crushing pressure and searing heat are not the only forces shaping the hellscape of Venus. The planet presents us with another profound and deeply counterintuitive mystery, one that operates high above its scorching surface. While Venus itself rotates at a glacial pace, taking 243 Earth days to complete a single spin and making its day longer than its year, the atmosphere above it is caught in a frenzy of motion. High in the Venusian cloud decks, the entire atmosphere is racing around the planet in a phenomenon known as superrotation, achieving a full circumnavigation in a mere 4 Earth days. This means the winds screaming through the upper atmosphere are traveling at hurricane force, clocking speeds of over 224 miles per hour, and they are doing so continuously, flowing much faster than the planet rotates beneath them. Imagine a world where the very air is in a perpetual planet-wide sprint, forever outstripping the ground below. Unraveling the mechanism behind this atmospheric paradox has been a major focus of planetary science. The leading theory points to a complex transfer of energy and momentum. Heat from the sun, absorbed primarily at the equator, creates massive convection cells in the thick atmosphere. As hot air rises and cooler air sinks, these circulating masses of gas are deflected by the planet's slow rotation, a force known as the Coriolis effect. However, on Venus, this process is turbocharged by thermal tides. The sun's intense heating on the day side of the planet causes the atmosphere to bulge outward, creating a massive, traveling wave of pressure that courses from the day side to the night side. This daily thermal tide interacts with the planet's surface, which acts like a drag on the lower atmosphere and with waves generated by its mountainous highlands. All these factors conspire to push momentum from the lower, slower atmosphere up into the higher, faster-moving cloud layers, effectively giving the upper atmosphere a constant push, like a planetary scale engine perpetually feeding energy upward to maintain this incredible speed. This super-rotating atmosphere has dramatic consequences for the planet's climate and weather. It creates a remarkably uniform temperature distribution from the equator to the poles, preventing the stark temperature gradients we see on Earth. It also means that any probe or hypothetical craft flying in those upper cloud layers would be carried along in this relentless river of wind, experiencing a constant, roaring gale while seeing the sun rise and set against a background of a nearly stationary landscape far below. This bizarre disconnect between the ground and the sky serves as a powerful reminder that planets are integrated systems, where heat, rotation, and topography can interact in ways that produce global phenomena utterly alien to our terrestrial experience. The superrotation of Venus is more than just a meteorological curiosity. It is a masterclass in fluid dynamics on a planetary scale, showing us that even in a world of crushing pressure and infernal heat, the atmosphere can still take on a life of its own, moving to a rhythm set not by the spin of the world below, but by the complex and relentless dance between a star and its planetary companion. Leaving behind the tempestuous atmospheres of gas giants and the frozen oceans of distant moons, we venture now to the scorched innermost planet, a world that has long guarded a secret deep within its metallic heart. Welcome to Mercury, a small, cratered world that seems at first glance to be a simple, geologically dead sphere of rock and iron, baked by its proximity to the Sun. But appearances, especially in planetary science, can be profoundly deceptive. For such a small planet, only slightly larger than our own moon Mercury, possesses a magnetic field, a discovery that sent shockwaves through the scientific community. A global magnetic field is typically generated by what's known as a dynamo, a churning, molten, electrically conductive core spinning within a planet. We see this on Earth with its large, molten iron core, but Mercury is so small that, according to all conventional models, its core should have cooled and solidified completely billions of years ago, shutting down any dynamo and leaving it magnetically dead, just like Mars and our moon. The fact that it has a field, albeit a weak one, only about 1% the strength of Earth's, meant that something unusual and unexpected was happening deep inside this tiny world. The leading theory to explain this paradox is as elegant as it is strange. Mercury's core is creating its own kind of weather. Scientists propose that Mercury may have a unique layered structure. Its core isn't entirely molten. Instead, it's thought to be like a cosmic snow globe, but one filled with molten iron instead of water. The very outer portion of the liquid iron core is likely enriched with a lighter element like sulfur, which lowers its melting point. As the entire planet slowly cools over billions of years, the temperature at the top of this molten core drops just enough for pure iron to begin to crystallize out of the liquid mixture. Picture this: in the profound darkness and pressure at the heart of Mercury, tiny flakes of solid iron are forming like metallic snow. These iron crystals, being denser than the surrounding liquid, would then begin to slowly sink, drifting downward in a gentle, continuous shower toward the planet's center. This downward snowfall of solid iron is not just a static process, it is a dynamic engine. As the iron snow falls, it leaves behind the lighter, sulfur-rich liquid. This leftover liquid becomes buoyant and starts to rise. The entire process sets up a slow, churning convection within the core, with light material rising and heavy material sinking. It is this large-scale movement of an electrically conductive fluid, the liquid iron alloy, that is thought to power Mercury's weakened but persistent magnetic dynamo. This iron snow model beautifully resolves the mystery of the planet's magnetic field, providing just enough energy to keep the dynamo sputtering along without requiring the core to be fully and turbulently molten. The implications of this are staggering. It suggests that the internal lives of planets are far more varied and complex than we once believed. A process we might associate with a winter's day on Earth is occurring in the searing hot interior of the closest planet to the Sun, governing the creation of a global magnetic shield. This magnetic field, however weak, is critically important. It offers a tenuous defense, diverting the worst of the Sun's powerful solar wind and creating a small, compressed magnetosphere that helps protect Mercury's surface from direct bombardment by high-energy particles. So, this tiny, sun-scorched world, once thought to be a simple relic, is now understood to be a place of hidden, dynamic activity, where a slow-motion metallic blizzard rages in the perpetual darkness below, silently generating a force field that has defied our expectations and deepened our appreciation for the hidden wonders of the solar system. Even as we grapple with the invisible fury of Jupiter's radiation belts, we find that Saturn holds its own masterpiece of atmospheric oddity, a feature so geometrically perfect it seems to defy the very nature of chaotic weather. High above the cloud tops at Saturn's North Pole, a stunning and persistent hexagonal jet stream holds court, a six-sided weather pattern of such precision it looks as though it was drawn by a cosmic geometer. This isn't a small feature. Each side of the hexagon is longer than the diameter of Earth, making the entire structure large enough to fit nearly 4 of our entire planet within its boundaries. First glimpsed by the Voyager probes in the 1980s and later studied in exquisite detail by the Cassini spacecraft, this hexagon has remained stable for decades, a fixed and rotating feature in Saturn's turbulent atmosphere. The winds that race along its perimeter are staggering, screaming at speeds of around 200 miles per hour. yet the overall shape remains locked in place, a colossal, slow-rotting honeycomb cell etched into the planet's sky. The formation of such a perfect geometric shape in a dynamic fluid environment is a puzzle that has captivated planetary scientists. The leading hypothesis suggests that the hexagon is a manifestation of a phenomenon known as a standing wave. Here on Earth, you can create a standing wave by vibrating a plate covered with a thin layer of liquid. Under the right conditions, the liquid will settle into a stable, geometric pattern. On a planetary scale, something similar may be happening deep within Saturn's atmosphere. The theory posits that differences in the speeds of Saturn's internal atmospheric currents, coupled with the planet's rapid rotation, a day on Saturn is only about 10.5 hours, create instabilities. These instabilities can generate a specific type of wave called a Rossby wave, which gets trapped at a particular latitude around the North Pole. The mathematics of fluid dynamics in a rapidly rotating sphere show that such a trapped wave can naturally take on a polygonal shape, and in Saturn's specific conditions, that shape appears to be a hexagon. It's essentially a self-organizing system where the chaotic motions of the atmosphere are coerced into an orderly pattern by the fundamental physics of rotation and shear. This makes the hexagon not a solid structure, but a colossal, swirling river of air whose path is defined by a standing wave pattern, a roadmap of atmospheric physics written on a planetary scale. Intriguingly, during Saturn's long northern winter, the entire polar region, including the hexagon, was plunged into darkness for years. But when the sun finally rose with the arrival of spring, Cassini's cameras revealed that the hexagon was not only still there, but it acted as a towering barrier, creating a veritable fortress in the sky. The inside of the hexagon developed its own unique weather, with a complex, rotating vortex at the very center and a remarkable difference in atmospheric composition and haze particles compared to the outside. This showed that the hexagon is not just a surface pattern. It is a deep-rooted, towering structure that extends hundreds of kilometers down into the atmosphere, effectively isolating the air within its walls and creating a distinct meteorological cell. The enduring mystery and beauty of Saturn's hexagon serve as a powerful testament to the universality of physical laws. It demonstrates that the same principles that govern the formation of swirling patterns in a cup of coffee or the vibration of a guitar string can, when scaled up to the size of a gas giant, produce one of the most breathtaking and enigmatic sights in our solar system. It is a permanent reminder that nature, in all its apparent chaos, has a hidden fondness for order, and that the most profound artistry in the cosmos is often written not in stone but in wind. As we move from the intimate, violent landscapes of planets and moons, we must now expand our perspective to a scale that is almost impossible to comprehend. We are leaving the confines of our solar system and even our galaxy to confront one of the most profound and unsettling discoveries in all of cosmology, the existence of nothingness on a cosmic scale. In the northern constellation of Boötes, the herdsman, lies a region of space so empty, so profoundly vacant, that it has earned the name the Boötes Void. This is not a simple gap between stars. It is a cosmic desert of almost unimaginable proportions, a spherical region of the universe spanning a staggering 250 million light-years across. To grasp that scale, try to picture a bubble so vast that if you placed our entire Milky Way galaxy at its center, you would have to travel for tens of millions of years at the speed of light in any direction before you encountered another major structure. In a universe that is overwhelmingly structured into a vast cosmic web of galaxies, filaments, and clusters, the Boötes Void is a gaping hole, a universe within a universe that is almost completely empty. When it was first identified in the 1980s, astronomers were stunned to find that this colossal volume contained only a few dozen galaxies, where according to the average density of the universe, they expected to find thousands. This terrifying scarcity challenges some of our most fundamental ideas about how the universe formed and evolved after the Big Bang. The standard model of cosmology suggests that matter in the early universe was not distributed perfectly evenly. Tiny quantum fluctuations were magnified by gravity over billions of years, drawing matter together into the dense knots we see as galaxy clusters and leaving behind the emptier voids. But the Boötes void is so exceptionally large and so empty that it pushes this model to its limits. How could gravity have cleared out such an immense volume without leaving behind more of a trace? It's as if a giant celestial plow came through and swept the area clean of galaxies, a process that defies easy explanation and suggests that either our understanding of the initial conditions of the universe is incomplete, or that there are more powerful, unknown forces at work in shaping the cosmos. The few galaxies that do exist within the void are fascinating in their own right. They are isolated island universes adrift in a sea of darkness, without the frequent gravitational interactions and mergers that galaxies in clusters experience. These lonely inhabitants are thought to be quieter, older, and more quiescent, evolving in solitude over cosmic time. They are cosmic hermit kingdoms, their stellar populations aging without the dynamic upheavals that reshape galaxies in more crowded neighborhoods. Their very existence, however sparse, provides crucial clues. The distribution of these few galaxies might trace the faint, ghostly skeleton of the filament that once ran through this region before most of its matter was siphoned away by the gravitational pull of the surrounding superclusters. The Boötes void forces us to confront the sheer randomness and potential imbalance of the cosmos. It stands as a humbling reminder that for all the patterns we observe, the universe is also capable of producing staggering anomalies, regions of profound emptiness that stretch our models of reality to the breaking point. It is a monument to the fact that the cosmos is not just defined by the brilliant fires of stars and galaxies, but also by the vast, dark, and silent spaces in between. From the silent, geometric perfection of Saturn's hexagon, we now plunge into a world of pure, unrelenting geological chaos. Imagine a celestial body so thoroughly tormented by gravity that its entire surface is effectively turned inside out on a regular basis. This is Io, the innermost of Jupiter's 4 large Galilean moons, and it holds the undisputed title of the most volcanically active body in our entire solar system. While our own moon is a quiet, cratered relic, Io is a dynamic, fiery inferno, a world whose skin is constantly being stretched, squeezed, and fractured by forces far beyond its own control. The engine behind this spectacular violence is not internal radioactive decay, as it is to a large extent on Earth, but an external source of almost unimaginable power, the gravitational field of Jupiter. Io's orbit around the giant planet is not a perfect circle, it is slightly elliptical. This small eccentricity is the key to its hellish existence. As Io travels along this lopsided path, its distance from Jupiter changes constantly. When it is closer, Jupiter's gravity pulls on it with significantly more force than when it is farther away. This varying pull causes the very body of the moon to flex. The solid ground beneath your feet, if you could stand there, would actually rise and fall by as much as 100 meters with each orbit, a tidal bulge of rock that sweeps across the globe like a planetary-scale heartbeat. But this is only half of the story. Io is not alone in its dance around Jupiter. It is locked in an orbital resonance with its sister moons, Europa and Ganymede. For every one orbit that Ganymede completes, Europa completes 2, and Io completes 4. This precise, repeating rhythm means that the 3 moons regularly tug on each other with their own gravity, reinforcing the elliptical shape of Io's orbit and preventing it from settling into a more circular and therefore more peaceful path. The combined effect is a continuous, intense gravitational tug of war. Jupiter tries to pull Io into a sphere while the other moons constantly pull it out of shape. This relentless kneading generates an immense amount of friction deep within Io's interior. The energy from this friction is converted directly into heat, on a scale so vast that it melts a significant portion of the Moon's silicate mantle, creating a global subterranean ocean of magma. This subsurface ocean of molten rock is the source of Io's spectacular volcanism. The internal pressure forces this superheated magma up through faults and fractures in the brittle, rocky crust, resulting in volcanic eruptions of epic proportions. These are not like the eruptions we see in Hawaii or at Mount St. Helens. Io's volcanoes can spew plumes of sulfur and sulfur dioxide hundreds of kilometers high enough to escape the Moon's weak gravity and paint its orbit with a donut-shaped cloud of ionized gas known as the Io plasma torus, which constantly feeds and re-energizes Jupiter's lethal radiation belt. The surface of Io is a constantly changing palette of yellows, oranges, reds, and blacks, a color scheme dominated by various forms of sulfur and silicate lava. Vast lava flows, some hotter than any seen on Earth in billions of years, carve rivers of incandescent rock across the landscape. Calderas or volcanic pits pockmark the surface, and towering volcanic plumes create umbrellas of fine debris that fall back to the surface like snow, but a snow made of frozen sulfur dioxide. There are no impact craters visible on Io. They are erased by new lava flows and volcanic deposits in a matter of decades, making its surface the youngest in the solar system. This world is literally resurfacing itself before our eyes, a process driven not by its own internal fire, but by the rhythmic, inescapable dance of gravity with its celestial neighbors. Io stands as the ultimate testament to the power of tidal forces, a world so thoroughly cooked from the outside in that it has become a permanent, raging testament to the dynamic and often violent relationships that govern the cosmos. But if the vast, empty expanse of the boomerang void shows us the universe's capacity for nothingness on a galactic scale, then the object that shares a similar name reveals an entirely different kind of extreme, a deep, penetrating cold that is the very antithesis of stellar fire. Drifting through the constellation of Centaurus, some 5,000 light-years from Earth, is the Boomerang Nebula, a pre-planetary nebula that currently holds the undisputed title of the coldest known natural place in the entire universe. This isn't just a bit colder than a winter's night on Earth. We are talking about a region of space where the temperature has been measured at a staggering 1 degree Kelvin, which is just a single, fragile degree above absolute zero. To put that in perspective, the background temperature of the void of space itself, the leftover warmth from the Big Bang, is a relatively balmy 2.7 Kelvin. So the Boomerang Nebula is significantly colder than the universe's baseline, a profound and counterintuitive state that seems to defy the very flow of energy. The secret to this deep freeze lies not in a lack of heat, but in a specific, violent process happening at the nebula's heart. At its center lies a dying star, a red giant in its final death throes. In this late stage of stellar evolution, such stars begin to shed their outer layers into space. What makes the Boomerang special is the sheer speed and volume at which it is losing its mass. This central star is ejecting material at a phenomenal rate, blowing gas outward at speeds of over 164 kilometers per second. This rapid expansion is the key to the cooling effect, working on a principle you experience every day. When you use a common aerosol can, you might notice the nozzle gets cold. That's because as the compressed gas inside expands rapidly upon release, its molecules spread out and do work against the surrounding atmospheric pressure, which causes them to lose kinetic energy and thus heat. The Boomerang Nebula is essentially a cosmic version of this on a staggering, stellar scale. Its gas is expanding so quickly and into such a vast volume that it undergoes an extreme version of this adiabatic cooling, dropping the temperature to that record-breaking low. The nebula itself is the beautiful and ghostly evidence of this process. We see a distinctive bow tie or double-lobed shape, which is created by a very dense, very thin ring of dust and gas pinching the outflowing material into that hourglass form. This structure acts like a nozzle, further accelerating the gas and enhancing the cooling effect. Because this is a pre-planetary nebula, the central star has not yet become hot enough to ionize the ejected gas and make it glow on its own. Instead, the beautiful, faint blue light we see is starlight reflected off of microscopic dust grains within the nebula. This object gives us a fleeting glimpse into a very brief and dramatic phase of a star's life, a phase that lasts only a few thousand years. In cosmological terms, this is the blink of an eye, a momentary chill before the central stellar core heats up and transforms the nebula into a fully fledged planetary nebula, illuminating it from within and warming its surroundings once more. For now, however, the Boomerang Nebula stands as a unique laboratory of physics, a place where the simple act of expansion has created a pocket of the cosmos that is colder than anywhere else we have ever found, a silent, freezing monument to the dynamic and often counterintuitive processes that sculpt the lives and deaths of stars. If you thought the slow, crushing pressure of Venus was intense, or the frozen methane seas of Titan were strange, prepare yourself for a world where the very concept of weather is redefined as a form of permanent horizontal violence. 64 light-years away in the constellation of Vulpecula, the Fox orbits a planet known as HD 189733b. This is a gas giant, often called a hot Jupiter, due to its immense size and its absurdly close orbit to its parent star, completing a full year in just 2.2 Earth days. That proximity is the first ingredient in this recipe for atmospheric hell. The planet is tidally locked, meaning one side constantly faces the star, broiling under perpetual, scorching daylight, while the other is locked in eternal, frigid night. This creates the most extreme temperature gradient imaginable on a planetary scale. The day side is heated to a searing 1,700 degrees Celsius, hot enough to melt aluminum, while the night side, though still brutally hot by our standards, is hundreds of degrees cooler. It is this staggering difference, a thermal cliff between day and night, that acts as the engine for the planet's most infamous feature. The superheated atmosphere on the day side expands and rises violently, screaming toward the cold night side in a desperate attempt to equalize the pressure. This generates supersonic winds that have been clocked at speeds in excess of 5,400 miles per hour. To put that in perspective, the most powerful tornadoes on Earth have wind speeds of just over 300 miles per hour. The winds on HD 189733b are over 17 times faster. They don't howl or roar. They are a continuous, supersonic shockwave of gas ripping across the planet's surface. But the wind itself is only the beginning of the horror. The atmosphere of this world is rich in silicates, the same minerals that make up sand and glass on Earth. In the blistering heat, these silicates vaporize, becoming a gaseous component of the atmosphere. But as these vaporized particles are carried by the incredible winds from the day side into the relative cold of the transition zone to the night side, they don't just slow down. They undergo a rapid and terrifying phase change. They condense. Instantly, they form into microscopic particles of molten glass. This creates a global, horizontal blizzard of scorching, razor-sharp glass shards flying at thousands of miles per hour. This is not a gentle rain that falls from the sky. It is a relentless, sideways scouring tempest. Any object or structure on the surface would be sandblasted into oblivion in an instant, polished away by a storm that never, ever ceases. The very sky is a weaponized abrasive, a shimmering, deadly haze of superheated silica. Observations from the Hubble Space Telescope have not only detected these silicates in the planet's atmosphere, but have also started to map its weather patterns in a stunning feat of remote sensing. By analyzing the light from the parent star as it filters through the planet's atmosphere during transits, scientists can determine both the composition and the dynamics of this alien air. They have confirmed the presence of these silicate clouds and have even begun to track the planet's jet streams, confirming the models that predict these unimaginable wind speeds. This world offers no refuge, no calm eye in the storm. It is a monument to atmospheric fury, a place where the fundamental forces of heat and pressure have conspired to create a permanent global sandstorm. If the sand were made of molten glass traveling at 7 times the speed of sound. It stands as a visceral reminder that the universe is not merely a collection of peaceful, twinkling lights, but a crucible where nature can forge environments of such sheer, violent intensity that they defy all terrestrial comparison. While the universe is filled with worlds of fire and ice, there are events so powerful and so fleeting that they dwarf even the most extreme planets. To witness one of these, we must turn our attention to the violent final dance of the universe's densest objects, the collision of 2 neutron stars. These are the collapsed cores of massive stars that went supernova, but were just shy of becoming black holes. A single teaspoon of neutron star material would weigh billions of tons, a mind-boggling density where atoms themselves have been crushed into a sea of neutrons. When 2 of these cosmic cannonballs, locked in a decaying orbit, finally spiral into each other, they unleash a cataclysm of almost unimaginable ferocity, an event that forges the very elements that make up our world in a blaze of cosmic creation. The initial collision sends ripples through the fabric of space-time itself, gravitational waves that we can now detect here on Earth, but that is just the opening act. The real spectacle is what astronomers call a kilonova, a brilliant flash of light 1,000 times brighter than a typical nova. For a few glorious days, this explosion outshines entire galaxies, and within its heart, it is conducting the most extreme alchemy in the cosmos. This is where the universe manufactures its heaviest and most precious elements. For a long time, scientists were puzzled about the origin of elements heavier than iron. Normal stars can fuse elements up to iron in their cores, but creating anything heavier requires a massive input of energy, a process known as rapid neutron capture. In the chaotic seconds following a neutron-star merger, vast clouds of free neutrons are blasted into space. These neutrons are then captured at an incredible rate by atomic nuclei, building them up into heavier and heavier elements in a frantic chain reaction. It is in this cosmic maelstrom that elements like gold, platinum, uranium, and iodine are born. The very gold in a wedding ring or the platinum in a catalytic converter was most likely forged in the furious aftermath of 2 dead stars colliding billions of years ago. This single event solved a long-standing mystery, providing the missing piece for our understanding of the cosmic origin of the elements. The discovery of a neutron-star merger in 2017 was a landmark moment for astronomy. For the first time, we not only heard the gravitational wave chirp of the collision, but also saw the resulting kilonova with telescopes across the electromagnetic spectrum. The data confirmed the theoretical predictions spectacularly, observing the signature of heavy elements being synthesized in real time. The calculations are staggering. A single merger can produce an amount of gold and platinum many times the mass of our entire planet, scattering these newly forged elements across the galaxy to be incorporated into future generations of stars, planets, and eventually, perhaps, life. So these cataclysmic events are not merely destructive, they are profoundly creative. They are the cosmic forges that seed the galaxy with the building blocks of planets and the very atoms that make up our bodies. We are, in a very literal sense, stardust, but the gold in our jewelry and the uranium that powers our reactors are the children of something far more violent and exotic, the ashes of a kilonova, a testament to the fact that from the most extreme destruction, the universe creates the foundations for everything we know. But to truly understand the raw material forged in a neutron star collision, we must first take an impossible journey to the surface of one of these stellar corpses. Imagine a world where the very laws of physics are pushed to their absolute breaking point, a realm of such incomprehensible density that it redefines our understanding of matter itself. This is the reality on a neutron star, formed from the collapsed core of a massive star after a supernova explosion, A neutron star packs more than the mass of our entire sun into a sphere only about 12 miles across. To grasp that absurd scale, picture compressing a mountain range the size of Mount Everest into a single sugar cube. That is the level of density we are confronting. The gravitational pull on the surface is correspondingly monstrous, roughly 200 billion times stronger than the gravity we feel on Earth. This force is so overwhelming that it fundamentally alters the nature of matter. Atoms, which are mostly empty space, cannot exist here. The immense gravity crushes the atoms, forcing the electrons into the atomic nuclei, where they combine with protons to form neutrons. The entire star becomes a gigantic nucleus, a sea of neutrons packed shoulder to shoulder, which is why a single teaspoon of this material would weigh an astonishing billion tons back on Earth. You could not lift it with every rocket ever built. Its weight would simply plunge it through the planet's crust as if the ground were water. The surface of this bizarre world is just as strange as its interior. Contrary to what you might expect, it isn't a formless, molten blob. The incredible pressure at the surface actually squeezes the material into a state known as a Coulomb crystal, forming an astonishingly perfect and incredibly smooth crystalline crust. This crust is thought to be a lattice of atomic nuclei, incredibly rich in neutrons embedded in a flowing ocean of superfluid neutrons. It's a solid, but unlike any solid we know. It is billions of times stronger than steel, a perfect, unyielding shell forged by the universe's most powerful press. This leads to one of the most counterintuitive features of a neutron star, its topography. On Earth, gravity allows for massive geological structures like the Himalayas, which rise nearly 9 kilometers into the sky. On a neutron star, that same gravity is so unforgiving that it tolerates almost no imperfections. The highest possible mountains on a neutron star are not grand, sprawling ranges, but tiny, millimeter-high ripples in the crystalline crust. These minuscule bumps are formed by the star's powerful magnetic field straining against the crust, creating stresses that push the unimaginably dense material upward by just a fraction of an inch. A mountain 1 centimeter high is a physical impossibility. The gravity would instantly flatten it, flowing the ultra-dense material back into a near-perfect sphere. This surface is also a place of terrifying tension. The crust is not a single, seamless shell. It is under immense strain from the star's rotation and its magnetic field. Occasionally, this strain becomes too much to bear and the crust cracks. This event, known as a starquake, is one of the most violent phenomena in the universe. When a section of this billion-ton strength crust fractures and shifts by just a few centimeters, it releases more energy than our sun will emit over a period of 100,000 years. This energy is released in a flash of gamma rays and X-rays, a starquake that can be detected from thousands of light years away, momentarily outshining entire galaxies in high-energy light. So the surface of a neutron star is a place of profound contradictions, a solid crust that is smoother than any mirror we could ever polish, dotted with mountains no taller than a grain of sand, and capable of unleashing planet-shattering convulsions from the slightest shift. It is a world built not from rock and metal, but from the fundamental building blocks of matter, compressed into a state that exists nowhere else in the cosmos, a perfect laboratory for testing the laws of physics under the most extreme conditions imaginable. And while the colossal gravity of a neutron star creates a uniquely hellish surface, there exists an opposing cosmic force capable of wielding gravity not as a prison, but as a weapon of propulsion, one that can eject entire stars from their galactic homes on a one-way trip into nothingness. These are the hypervelocity stars, the cosmic runaways of the galaxy, and their origin story is one of the most dramatic gravitational events imaginable. To be flung from the Milky Way, a star must achieve a speed greater than the galaxy's escape velocity, which is a staggering 1.3 million miles per hour. The stars we are talking about often travel far faster than this, some clocked at over 2 million miles per hour. At such speeds, a star could travel from the Earth to the Moon in a mere 5 minutes. The primary engine for this stellar catapult is the supermassive black hole that lurks at the very center of our galaxy, known as Sagittarius, a star. Most stars in the galactic core orbit this monstrous object in stable, if highly elliptical, paths. But occasionally, a binary star system, a pair of stars orbiting each other, will wander too close to the black hole's event horizon. This is where the cosmic slingshot, known as the Hill's mechanism, takes over. The black hole's overwhelming gravity exerts a vastly different pull on the two stars. The star closer to the black hole is gripped far more intensely than its companion. This difference in gravitational force, a tidal force of unimaginable power, violently rips the binary pair apart. One of the stars is captured by the black hole, falling into a tight, doomed orbit, while the other is flung away at an incredible velocity, as if from a gigantic sling. The energy for this phenomenal launch comes directly from the orbital energy of the original binary system, which is transferred almost entirely to the ejected star in a single gravitational whiplash. The trajectory of these stars is their eternal sentence. Once ejected, they do not slow down or curve back. They travel in almost perfectly straight lines, racing outward through the galactic disk and halo, never to return. They are destined to become intergalactic wanderers, solitary beacons sailing through the immense dark voids between galaxies. Their future is one of profound isolation. They will leave the light and structure of the Milky Way far behind, entering a realm where the nearest star is hundreds of thousands of light years away, and the night sky would be dominated not by a band of stars, but by the fading collective glow of distant galaxies. The discovery of these stars in the 2000s was a monumental confirmation of theoretical predictions and provided us with a unique opportunity. By tracing the path of a hypervelocity star backward across the sky, astronomers can, in principle, pinpoint its origin right back to the galactic center, offering us an indirect but powerful probe of the environment right around our supermassive black hole. It tells us about the population of binary stars that live in that chaotic region and the dynamic processes that govern the heart of our galaxy. Furthermore, studying these stars themselves is fascinating. They are not all the same. Some are massive, hot blue stars, while others are smaller, sun-like stars. Their composition and temperature tell the story of their origins before they were so violently exiled. They are celestial archaeologists carrying the chemical fingerprint of the galactic center out into the hinterlands. The existence of hypervelocity stars paints a picture of a galaxy that is not a static island of stars, but a dynamic ecosystem where cosmic violence can create celestial nomads, casting them out on eternal journeys into the cold, immense silence between the islands of light. Yet for all the violence of stellar collisions and the incredible speeds of hypervelocity stars, there exists an even more profound form of exile in the cosmos, a fate of absolute solitude and perpetual night. We now turn our attention to the ultimate orphans of the galaxy, rogue planets. These are not planets orbiting a star, not even one flung away like a hypervelocity star. These are entire worlds, some as large as Jupiter, others as small as Earth, that have been completely ejected from their home solar systems and now drift alone in the deep, cold emptiness between the stars. Their existence is one of profound isolation. Imagine a world with no sunrise, no sunset, no day, and no year. The sky is not blue, nor is it black with pinpoint stars. It is an endless, starless void, punctuated only by the faint, distant glow of far-off galaxies. The only light comes from these incredibly remote sources, offering no warmth, no color, and no changing of the seasons. The surface temperature on such a world without a star to warm it plummets to just a few degrees above absolute zero, a deep and penetrating cold that would freeze any atmosphere solid, creating a surface of barren, airless rock or ice more desolate than anything in our own solar system. The journey to this lonely state is typically a violent one, a gravitational accident of cosmic proportions. In the chaotic early days of a planetary system, when giant planets are still migrating and settling into their orbits, close gravitational encounters can occur. A smaller planet like an Earth straying too close to a gas giant like Jupiter can be slingshotted with such force that it achieves escape velocity, breaking free from its star's gravitational pull entirely. Alternatively, in a system with multiple large planets, a complex gravitational dance can eject one of the participants, casting it out into the interstellar darkness. Once free, these planets are on a one-way trip to nowhere, sailing through the galaxy on a trajectory that will almost certainly never bring them close to another star again. They are the true dark sailors of the cosmos, invisible to conventional telescopes because they emit no light of their own and reflect none. We only know they exist through the rare and clever technique of gravitational microlensing. When one of these dark wanderers passes almost perfectly in front of a distant background star, its gravity acts as a lens, bending and magnifying the star's light for a brief period. From that tiny, telltale brightening, astronomers can infer the rogue planet's mass and its presence. These observations suggest a staggering reality. There may be billions, even trillions, of these lone worlds drifting through our galaxy, vastly outnumbering the stars themselves. But the most astonishing possibility lies hidden beneath their frozen surfaces. While the surface of a terrestrial rogue planet is a frozen wasteland, it may not be entirely dead. The planet's interior could still be warm, heated by the residual heat from its formation and the slow, radioactive decay of elements in its core. This internal warmth could be enough to maintain a vast, global ocean of liquid water trapped beneath a thick, icy crust, much like the subsurface oceans we believe exist on moons like Europa and Enceladus. In this scenario, a rogue planet becomes a dark, mobile aquarium, a sealed biosphere traveling through the galaxy. Life, if it began before the planet was ejected or somehow originated in the deep, chemosynthetic environment around hydrothermal vents on the ocean floor, could potentially survive for billions of years in this isolated, sunless sea. The energy for an ecosystem wouldn't come from photosynthesis, but from geothermal heat and chemical reactions between the water and the rocky seabed. This transforms our understanding of where life could exist. We have always looked for planets in the habitable zone around stars where liquid water can exist on the surface. But rogue planets suggest that life could be far more widespread, hidden in the absolute darkness of interstellar space, thriving in warm, subsurface oceans completely independent of any star. These dark, wandering worlds are therefore not merely cosmic curiosities. They are potential arcs carrying the possibility of life through the immense, empty stretches of the galaxy, their internal oceans serving as insulated sanctuaries against the eternal cold outside. They represent a form of resilience we are only beginning to comprehend, a testament to the idea that even in the most isolated and seemingly inhospitable corners of the universe, the conditions for life might quietly persist, completely unseen and unknown. And now we arrive at a phenomenon of such raw, astronomical power that it can outshine not just stars but entire galaxies, a beacon of destruction so brilliant it can be seen from the edge of the observable universe. To understand this, we must approach the ultimate cosmic predator not as a simple vacuum cleaner in space, but as the engine of the most energetic and luminous engines in existence, the supermassive black hole. These are not the stellar mass black holes formed from collapsing stars. These are monsters weighing in at millions or even billions of times the mass of our Sun, and they reside at the very heart of most galaxies, including our own Milky Way. But a dormant black hole is invisible. The true spectacle begins when it starts to feed. As a black hole's immense gravity pulls in gas, dust, and even entire stars from its surroundings, this material does not fall straight in. Instead, it forms a vast, swirling, incandescent vortex known as an accretion disk. Picture a hurricane of fire, but on a scale so immense that our entire solar system would be a mere speck within it. This is the cosmic blender, a place where the fundamental laws of orbital mechanics meet unimaginable friction and heat. The material in this disk is caught in a frantic spiral, orbiting at speeds approaching a significant fraction of the speed of light. The particles of gas and dust in the inner regions of the disk are moving vastly faster than those in the outer regions, and as they slide past one another, the resulting friction is astronomical. This friction, along with powerful magnetic fields tangled within the maelstrom, heats the material to staggering temperatures reaching millions of degrees. At such extremes, the matter doesn't just glow with visible light. It shines with an intense fury of X-rays and gamma rays, becoming a lighthouse beacon of high-energy radiation. The energy released in this process is almost beyond comprehension. While nuclear fusion in a star's core is incredibly efficient, converting about 0.7% of mass into energy, the process within an accretion disk can be dozens of times more efficient. As matter loses gravitational potential energy on its final plunge, a significant fraction of its mass is transformed directly into pure radiation according to Einstein's famous equation. This is the secret behind the awesome power of a quasar or quasi-stellar object. When a supermassive black hole is in an extremely active feeding phase, its brilliant accretion disk can become so luminous that it drowns out the combined light of every single star in its host galaxy. A single quasar can be thousands of times brighter than an entire galaxy like the Milky Way, making them the most persistently luminous objects in the entire cosmos. We can see their piercing light from over 13 billion light-years away, allowing us to look back in time to an era when the universe was young and such voracious black holes were more common. But the sheer intensity of the radiation creates another fascinating and hostile effect: radiation pressure. The light pouring out from the inner disk is so powerful that it actually pushes outward on the infalling material. This creates a delicate and dynamic balance. For matter to finally cross the event horizon and be lost forever, it must fight its way through this hurricane of outgoing energy. In many cases, this intense pressure actually halts the inflow of gas, effectively starving the black hole and regulating its own growth. This feedback mechanism is crucial to our understanding of how galaxies evolve, as the energy from these active black holes can blow away the gas needed to form new stars, effectively shutting down star formation in their host galaxies and shaping them into the elliptical galaxies we see today. Furthermore, not all the material is destined to fall in. Some of it is channeled and focused by the black hole's spin and its magnetic fields into two narrow, powerful jets that shoot out from the poles of the accretion disk perpendicular to its plane. These jets, composed of charged particles traveling at nearly the speed of light, can stretch for hundreds of thousands of light-years into intergalactic space, punching through the gas of the host galaxy and beyond. When one of these relativistic jets is pointed almost directly at Earth, we see an even more extreme and variable object known as a blazar, whose intense emission can fluctuate wildly over short periods. So the accretion disk is far more than just a pretty light show. It is a transformative cosmic engine. It is a place where gravity is converted into light with breathtaking efficiency, where the fate of entire galaxies can be decided, and where matter makes its final, furious stand before disappearing forever behind the veil of the event horizon. It stands as a brilliant testament to the fact that in the universe's most extreme environments, even the act of consumption can become an act of creation, illuminating the cosmos with a light that defies all scale and expectation. But the accretion disk represents just the outer turmoil of a black hole's influence. To confront its most personally terrifying aspect, we must now follow a hypothetical piece of that doomed material on its final one-way journey, moving past the disk's fury and toward the point of no return. This brings us to a phenomenon that sounds like science fiction but is a direct and gruesome consequence of the fundamental laws of gravity: spaghettification. The term itself is whimsical, but the reality it describes is a fundamental limit of physics, a process that would dismantle any object from a spacecraft to a star at the most basic atomic level. The driving force behind this bizarre stretching is not the sheer strength of the black hole's gravity, but rather its gradient, how drastically the force changes over a very short distance. Here's how it works. Gravity weakens with distance, and this is true even for a black hole. If you were falling feet first toward a stellar mass black hole, your feet would be significantly closer to the singularity than your head. Because gravity is so much stronger even a short distance closer to the center, your feet would be pulled with immensely greater force than your head. Your entire body would be subjected to an extreme and continuous stretching force, lengthening you like a piece of taffy. At the same time, the sides of your body, all converging toward the same central point, would be squeezed inward by this same radial gravity. The combination of this vertical stretching and horizontal compression is what gives the process its name. You would be stretched into a long, thin stream of atoms resembling a single strand of spaghetti. This isn't a gradual process that gives you time to contemplate your fate. It would happen with violent speed. For a stellar mass black hole, which might be only a few dozen kilometers across, the gravitational gradient is incredibly steep. The difference in pull between your head and your feet would become significant thousands of kilometers away from the event horizon. You would be torn apart well before you even reach the point of no return, your body and your ship unraveling into a stream of elementary particles spiraling into the abyss. However, the story changes dramatically with a supermassive black hole like the one at the center of our galaxy. Because these beasts are so colossally large, with event horizons millions of kilometers in diameter, the gravitational gradient at the event horizon is much more gentle. The difference in pull between your head and your feet at that point might be negligible. You could, in theory, cross the event horizon of a supermassive black hole completely unharmed, at least initially. The spaghettification point, where the tidal forces become lethal, lies far inside the event horizon for these gigantic black holes. This creates a profoundly unsettling scenario. You could cross the boundary from which no light or information can escape, still alive and conscious, only to be inevitably shredded into atoms deeper inside, where the gradient finally becomes unbearable. This process is not just a grisly thought experiment. It has real, observable consequences for larger objects. A star that wanders too close to a supermassive black hole will be torn apart by these same tidal forces in an event called a tidal disruption event. The black hole's gravity will pull more strongly on the side of the star facing it, stretching the star until it surpasses its own gravitational binding energy and ruptures. About half of the star's gaseous debris is then flung out into space, while the other half forms a temporary, brilliant accretion disk, creating a flare of radiation that astronomers can detect across the universe. Spaghettification, therefore, is a universal physical process, a stark demonstration that gravity is not a uniform force, but a field that can exert drastically different pulls on different parts of the same object. It represents the ultimate victory of gravity over every other force that holds matter together, from the chemical bonds in our bodies to the nuclear forces binding atomic nuclei. It is the final, inescapable physical deconstruction, a fundamental limit imposed by nature itself on how close any complex structure can ever get to the ultimate expression of gravity's power. But from the immense but steady pull of a supermassive black hole, we must now turn to a force of a very different kind, one that is transient, violent, and concentrated into an object small enough to fit inside a city. We have already explored the bizarre nature of neutron stars, But within that family of cosmic oddities exists a truly terrifying subspecies, the magnetar. These are neutron stars that take an already extreme environment and crank the dial to 11, specializing in one particular facet of physics to a degree that is almost fictional. If a typical neutron star's magnetic field is powerful, a magnetar's is apocalyptic. To understand the scale, we measure magnetic field strength in units called Gauss. A strong refrigerator magnet is about 100 Gauss. The Earth's protective magnetic field measures about half a Gauss. A typical neutron star boasts a field of a few trillion Gauss. A magnetar, however, possesses a magnetic field of 1,000 trillion Gauss or more. This is 1,000,000 billion times stronger than Earth's field, a concentration of magnetic energy so intense that it fundamentally alters the vacuum of space around it. This field is so powerful that it becomes a tangible, destructive force in its own right. If a magnetar were to appear as close to us as the Moon, its magnetic field would not just disrupt compasses. It would be instantly lethal. It would levitate you by manipulating the iron in your blood, and more surreally, it would scramble the very electromagnetic fields that hold your atoms together, effectively tearing you apart from the inside out. The popular science claim is not an exaggeration. From a distance of halfway across the Milky Way, around 20,000 light-years, a magnetar's flare could indeed electromagnetically scrub the magnetic strip from every credit card on Earth. The consequences for our technology-dependent civilization would be far more severe, inducing currents in power grids and satellites that would fry them on a global scale. The origin of this monstrous magnetic field is thought to be a perfect storm during the star's formation. When a massive star collapses to form a neutron star, its already existing magnetic field is compressed along with its matter. This alone amplifies the field tremendously in a process known as flux conservation. But theorists suggest that for a magnetar to form, an additional dynamo effect must occur in the first few seconds of the neutron star's life. If the newborn star is spinning rapidly enough, completing a full rotation in just a few milliseconds, the convecting, turbulent sea of neutrons and protons in its interior can act like a colossal generator, amplifying the magnetic field to those quintillion Gauss levels. This makes magnetars relatively rare and short-lived. Their immense magnetic fields decay over a period of about 10,000 years, a mere blink in cosmic time, as the energy is radiated away, powering their persistent X-ray glow and occasional violent outbursts. The most dramatic demonstrations of a magnetar's power are not its steady field, but its sudden starquakes. We've discussed how the crust of a neutron star is a rigid, crystalline structure under immense strain. On a magnetar, the magnetic field is so strong that it is actually woven into the very fabric of this crust, exerting a colossal stress upon it. As the field evolves and twists, it puts an unbearable strain on the star's rigid surface. Eventually, something has to give. The crust, stronger than steel, suddenly cracks and shifts. This is a starquake, but on a magnetar, it is a magnetic cataclysm. The energy released is not just seismic, it is primarily magnetic. The sudden rearrangement of the crust releases a vast amount of pent-up magnetic energy in an instant, triggering an enormous flash of radiation, a giant flare. For a fraction of a second, a magnetar in flare can outshine every star in our galaxy combined, but its light is not in the visible spectrum. It is an intense, deadly burst of gamma rays and hard X-rays. One such event from the magnetar SGR 1806-20 was detected in 2004. In just 0.2 of a second, it released more energy than our Sun has emitted over the last 250,000 years. It actually compressed Earth's ionosphere from a distance of 50,000 light-years, briefly altering the propagation of long-wavelength radio signals around the planet. These magnetar flares are so powerful that for years the strongest ones were mistaken for distant gamma-ray bursts, the universe's most energetic explosion since the Big Bang. They are a stark reminder that the cosmos harbors engines of destruction that operate not on the scale of nuclear fusion, but on the scale of magnetic annihilation, where the cracking of a stellar crust can send a shiver through the fabric of space-time itself and momentarily outshine entire galaxies. Venturing out past the ringed splendor of Saturn and the tempestuous might of Jupiter, we enter the true frontier of our solar system, a realm of dim, blue-green light and profound cold. Here, the distant sun is little more than a particularly bright star, providing negligible warmth to the two ice giants, Uranus and Neptune. While often lumped together, these twin worlds are far from identical, each possessing a unique and deeply strange personality forged in the freezing darkness. They are not gas giants like Jupiter and Saturn, which are composed mostly of hydrogen and helium. Instead, they are classified as ice giants, and their primary constituents are what scientists call ices, not just frozen water, but a slushy mixture of water, ammonia, and methane, existing under conditions of immense pressure that defy our everyday understanding of matter. The journey into one of these worlds begins as you descend through a relatively clear and calm upper atmosphere of hydrogen and helium. But as you go deeper, the pressure and temperature rise steadily, and you would soon find yourself immersed in an ocean. This is not an ocean of liquid water as we know it, but something far more exotic, a supercritical fluid. At a certain threshold of temperature and pressure, the distinction between a liquid and a gas blurs and then vanishes entirely. The substance becomes a supercritical fluid, possessing the density of a liquid but the expanding, penetrating properties of a gas. On Uranus and Neptune, this is the state of the vast water-ammonia ocean that makes up their bulk. You would be sinking through a hot, dense, and electrically conductive fluid that has no surface and no boundary between liquid and vapor. A churning, global sea that behaves unlike any body of water in our solar system. It is within this strange, inner ocean that one of the most fantastical weather phenomena in the cosmos occurs. The incredible pressures and temperatures, thousands of degrees Celsius and millions of times Earth's atmospheric pressure, rip apart the methane molecules that are mixed in with the water and ammonia. This process liberates carbon atoms. Under these extreme conditions, the carbon atoms are compressed with such force that they bond into the crystalline structure of diamond. Scientists believe that deep within the interiors of both Uranus and Neptune, it literally rains diamonds, not tiny specks, but diamonds potentially millions of carats in weight, forming a glittering hail that slowly sinks through the slushy ocean toward the planet's cores. It's a breathtaking thought. The cores of these distant blue worlds may be surrounded by a thick layer of solid diamond, a treasure forged not in a jeweler's workshop, but in the crushing heart of a planet. Beyond their astonishing interiors, the ice giants present another extreme that is written plainly across their faces, their axial tilt. A planet's tilt is what gives it seasons. Earth is tilted at a comfortable 23.5 degrees, leading to our regular, predictable spring, summer, fall, and winter. Uranus, however, takes this concept and turns it on its head, quite literally. This world is tilted a staggering 98 degrees, meaning it essentially orbits the sun on its side. Picture a rolling ball instead of a spinning top. This bizarre orientation leads to the most extreme seasonal patterns in the solar system. For a quarter of its 84 Earth-year orbit, one pole is pointed directly at the sun, experiencing 42 years of continuous daylight, while the other pole is plunged into a 42-year-long night of absolute darkness. The rest of the planet experiences a rapid, strange cycle of day and night as it rotates. Neptune, while tilted at a more conventional 28 degrees, still presents its own atmospheric mysteries. It is the windiest planet in our solar system, with gales roaring through its atmosphere at speeds surpassing 1,200 miles per hour, near the theoretical sound limit for its frigid, hydrogen-rich air. These supersonic winds, powered by internal heat left over from the planet's formation, create a dynamic and ever-changing atmosphere, complete with massive, dark storms like the famous Great Dark Spot witnessed by Voyager 2, a hurricane the size of Earth that appears and disappears unpredictably. The ice giants, therefore, stand as a testament to the diversity of planetary systems. They are worlds of profound internal alchemy, where supercritical oceans brew diamond hail, and of external celestial mechanics, where a planet can roll through its orbit, offering its poles decades of unending sun or shadow. They remind us that even in the cold, distant reaches of our own stellar backyard, the universe continues to operate on a scale of wonder and extremity that constantly challenges our imagination. Yet beneath the tranquil, frozen facade of this distant moon lies one of the most tantalizing secrets in our solar system. That remarkably smooth and youthful surface is not solid rock. It is a global, icy shell, and it hides a breathtaking reality below. Europa is now believed to harbor a global saltwater ocean, a body of liquid water trapped between its rocky mantle and its outer ice crust. The volume of this hidden sea is staggering. Estimates suggest it contains more than twice the total amount of liquid water found in all of Earth's oceans, lakes, and rivers combined. Imagine a world where a single, interconnected ocean wraps the entire globe, its depths hidden under a ceiling of ice that may be miles thick. This isn't a small, subsurface lake. It is a true world ocean, a mysterious abyss that has remained liquid for billions of years. The engine that prevents this vast water volume from freezing solid is the same tidal heating that torments its volcanic neighbor, Io. As Europa travels along its slightly elliptical orbit around Jupiter, the gas giant's immense gravity flexes the moon, stretching and squeezing its interior. This constant gravitational kneading generates immense friction and heat within Europa's rocky core, enough to keep the subsurface water in a liquid state. This process turns Europa into a giant, self-warming aquatic world, its hidden depths kept liquid by the relentless gravitational embrace of its parent planet. The ice shell itself is a dynamic and complex landscape. The long, dark lines that crisscross the surface, known as lineae, are believed to be fractures in the ice. They are thought to form as the tidal forces from Jupiter stress the ice, causing it to crack. Scientists hypothesize that these fractures could act as conduits, allowing water from the ocean below to well up, either partially melting the ice from beneath or even erupting onto the surface where it quickly freezes, creating the smooth, renewed terrain we observe. This process of ice tectonics would be somewhat analogous to plate tectonics on Earth, but playing out in a shell of frozen water instead of solid rock, constantly repaving the surface and erasing the evidence of ancient impact craters. The composition of this hidden ocean is another critical piece of the puzzle. Spectral observations from telescopes and spacecraft have detected salts, particularly magnesium sulfate, on Europa's surface, likely deposited there by water that has welled up from below. This strongly suggests the subsurface ocean is salty, much like Earth's oceans, but the most exciting detection has been of sodium chloride simple table salt. This is significant because on Earth, the presence of chloride is closely linked to hydrothermal systems on the seafloor. The possibility that Europa's ocean is not only vast and liquid, but also chemically rich and interacting with a rocky seabed, elevates it from a mere curiosity to a prime candidate in the search for life beyond Earth. The most revolutionary way to sample this alien ocean, however, doesn't require a lander or a drill. Just as with Enceladus, there is compelling evidence that Europa, too, vents its ocean into space. The Hubble Space Telescope has observed what appear to be intermittent plumes of water vapor erupting from the Moon's south polar region, towering perhaps 125 miles above the surface. While these plumes have been more elusive and harder to confirm than the spectacular jets of Enceladus, their potential existence is a game-changer. These plumes would be direct geysers from the subsurface ocean, blasting its contents through fissures in the ice shell and out into the vacuum. A future spacecraft flying through one of these plumes could analyze its composition with sophisticated instruments, tasting the water and searching within it for the complex organic molecules, salts, and perhaps even chemical signatures that could hint at biological processes. The upcoming Europa Clipper mission, set to arrive in the 2030s, is designed to do exactly that. It will conduct dozens of close flybys, mapping the ice shell in detail, probing the ocean's depth and salinity with ice-penetrating radar, and most importantly, scanning for and potentially flying through any active plumes to sample them directly. The ultimate question, of course, is whether this dark, deep, salty ocean could be a habitat for life. The recipe, as we understand it, is compellingly complete. Europa offers liquid water, a source of chemical energy from tidal heating and potential seafloor hydrothermal vents, and a rich soup of organic compounds delivered by impacting comets and asteroids over billions of years. On Earth, we find thriving ecosystems in the absolute darkness of the deep ocean, clustered around hydrothermal vents that spew mineral-rich superheated water. These communities of tube worms, giant clams, and bizarre microbes thrive entirely on chemical energy, completely independent of sunlight. The conditions on the seafloor of Europa could be strikingly similar. This transforms our image of this icy moon from a frozen wasteland into a potential oasis, a water world where life may have arisen and could persist in the perpetual darkness of a sunless sea, making Europa one of the most promising and compelling destinations in our entire quest to find out if we are alone in the universe. And just as we've seen worlds of water and ice and diamond, now consider a planet where the very rock itself is set ablaze. We journey to a star system over 480 light-years away to witness a type of hell so absolute it makes the volcanoes of Io look like gentle campfires. This is Co-Rho T7b, the first rocky exoplanet ever confirmed, and it is a textbook example of a lava world, a celestial body orbiting so close to its parent star that the concept of a solid surface becomes a fleeting memory. Imagine a planet where the ground beneath your feet isn't ground at all, but a churning, incandescent ocean of molten rock, a global sea of magma stretching from horizon to horizon under a sky of unimaginable violence. The proximity to its star is the sole architect of this inferno. Co-Rho T7b is locked in an orbit so tight that a full year, one complete trip around the star takes just 20 hours. To put that in perspective, this planet is more than 20 times closer to its sun than Mercury is to ours. This intimate dance has profound consequences, the most obvious being tidal locking. Just as our moon always shows the same face to Earth, Co-Rho T7b has a permanent day side that eternally faces the star and a permanent night side condemned to endless darkness. The temperature difference between these two hemispheres is astronomical. The day side is subjected to a continuous, blistering onslaught of stellar radiation, heating its surface to a temperature well over 2,500 degrees Celsius. That is hotter than the melting point of almost every known rock-forming mineral. At such extremes, the surface rock doesn't just melt, it literally boils. The landscape is a dynamic, rolling ocean of lava, with temperatures high enough to vaporize granite and basalt, turning solid stone directly into gas. This process creates a tenuous but utterly alien atmosphere, not of oxygen or nitrogen, but of mineral vapors. The very air on this world would be a mist of vaporized silicon, sodium, iron, and magnesium, rising from the lava seas like a metallic fog before condensing on the slightly cooler night side. This leads to a weather cycle of almost mythical brutality. On the scorching day side, rock vaporizes and rises into the atmosphere. Prevailing winds, generated by the extreme temperature difference between day and night, then carry these mineral vapors toward the frigid night side. As this hot, mineral-laden air crosses into the darkness where temperatures plunge to hundreds of degrees below zero, the vapors rapidly condense, but they don't form water droplets, they form microscopic particles of rock and metal. This results in a perpetual global rain of pebbles and dust, a hard, abrasive precipitation of solidified magma falling from the sky. On the night side, this rocky sleet would accumulate, potentially creating a surface of solidified lava, cold and dark, in stark contrast to the incandescent ocean just over the horizon. The entire planet is thus caught in a relentless cycle of vaporization and condensation, a geological and meteorological loop where the very crust is continually being recycled through the atmosphere. The forces at play on such a world are almost beyond comprehension. The gravitational pull from the nearby star creates immense tidal forces, flexing the planet's interior much like Jupiter does to Io. This tidal heating likely contributes to the volcanic activity, perhaps even helping to maintain the global magma ocean by stirring the planet's molten mantle. There is no sanctuary, no solid ground to be found on the day side. Any mountain range that dared to form would be swiftly melted back into the seething ocean, and any impact crater would be filled with lava in a geological instant. The surface is likely as smooth as a pond, but a pond of unimaginable heat and fury. Co-Rho T7b stands as a stark extreme in the planetary spectrum, a place where the line between a planet and a star's atmosphere becomes blurred. It shows us that the category of rocky planet encompasses not just familiar worlds like Earth and Mars, but also these scorched remnants, worlds that orbit so close to their suns that they have become permanent monuments to stellar fire. Their surface is a testimony to the awesome power of a star to utterly dominate and transform a world. And just as we've explored worlds forged in fire and sculpted by gravity, we now turn to one of the most beautiful and fleeting spectacles in the cosmos, a final farewell that paints the void with the colors of creation. These are planetary nebulae, the cosmic ghosts of dying stars, and their ethereal glow is the signature of a profound stellar transformation. Despite their name, they have nothing to do with planets. The term was coined by the astronomer William Herschel in the 1780s. Through his telescope, these faint, round objects resembled the greenish disks of distant gas giants like Uranus, which he had recently discovered. We now know they are something far more spectacular, the glowing funeral shrouds of sun-like stars in their final death throes. The story of a planetary nebula begins when a star, much like our own sun, exhausts the hydrogen fuel in its core. For billions of years, it had maintained a stable balance, using nuclear fusion to push outward against the immense crush of its own gravity. But when the core fuel runs out, this balance is shattered. The core begins to collapse under its own weight, heating up until it becomes hot enough to start fusing the next available fuel, helium, into carbon and oxygen. This ignites a helium flash, a violent and unstable event that causes the star to swell dramatically, transforming it into a red giant. In this bloated phase, the star's outer layers become incredibly tenuous and are only loosely bound by gravity. The real drama, however, is happening deep inside. The core, now a dense, hot ball of carbon and oxygen, is fiercely active. It undergoes a final, frantic burning phase, generating powerful pulses of energy and unleashing a torrent of ultraviolet radiation. This intense radiation and a relentless, supersonic stellar wind begin to blow the star's outer layers away into space, layer by layer, in a process that can take tens of thousands of years. What we see as the beautiful, intricate shell of a planetary nebula is this ejected material, the star's own atmosphere, now expanding into the interstellar medium at speeds of tens of kilometers per second. But why does it glow with such vivid colors? The secret lies in the exposed stellar core, which has now become a white dwarf. This Earth-sized remnant is unimaginably hot, with surface temperatures soaring to over 100,000 degrees Celsius. It bathes the expanding cloud of gas in a flood of high-energy ultraviolet light. This intense radiation energizes the atoms in the gas cloud, stripping away electrons in a process called ionization. When these electrons eventually reunite with the atoms, they release energy in the form of light, causing the entire nebula to fluoresce with its characteristic glow, much like the gas inside a neon sign. The specific colors depend on the chemical composition of the ejected gas. Red hues typically come from hydrogen, blue-green from doubly ionized oxygen, and other colors from elements like nitrogen and helium. The breathtaking complexity of their shapes, from delicate rings and intricate bubbles to bipolar structures that look like giant cosmic hourglasses or butterflies, is one of the greatest mysteries that modern astronomy has had to solve. A simple spherical star shouldn't produce such intricate formations. The answer lies in the dynamics of the star's final years. Many Sun-like stars are now believed to have companion stars or large planets orbiting very close to them. As the primary star swells into a red giant, it can actually engulf its companion. The smaller object then spirals inward through the star's outer layers, acting like a cosmic egg beater that stirs the gas and channels the outflow into two powerful jets perpendicular to its orbit. This process can create the magnificent bipolar lobes we see in nebulae like the Butterfly Nebula. Even without a binary companion, the star's own powerful magnetic fields, amplified during its turbulent death, can sculpt and collimate the outflowing winds, funneling the gas into symmetrical, jet-like structures and preventing it from expanding evenly in all directions. The life of a planetary nebula is tragically brief in cosmic terms. Within just a few tens of thousands of years, a mere blink of an eye compared to the star's 10-billion-year life. The expanding shell of gas becomes so large and diffuse that it fades from view, its material mixing with the interstellar medium. The white dwarf at its center will then slowly cool over billions of years, fading into a cold black dwarf. But in its brief, brilliant existence, a planetary nebula performs a crucial service to the universe. It is a cosmic recycling plant. Within that glowing gas are the heavy elements forged in the star's core, and during its violent death, carbon, nitrogen, oxygen, and more. These elements, scattered across space, will eventually become part of new generations of stars, planets, and ultimately the building blocks of life itself. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all once scattered into the galaxy by such an event. So when we gaze at the Cat's Eye Nebula or the Helix Nebula, we are not just looking at a beautiful cosmic ghost, we are witnessing the final, glorious act of a star, a process that seeds the galaxy with the very elements that make our own existence possible. It is a poignant and powerful reminder that in the cosmos, even death can be an artist, painting the void with the legacy of a star's long life and enriching the universe for eons to come. Now, let us turn our gaze from the explosive deaths of stars to the silent, continuous inferno that gives them life. To understand the true engine of a star, we must venture into its very heart, to a place of unimaginable force where the universe forges light from pure pressure. At the core of our own sun, a seemingly serene ball of gas from our distant vantage point, conditions exist that are so extreme they defy all human experience. Here, the pressure is an astronomical 250 billion times greater than the atmospheric pressure we feel at sea level on Earth. To even begin to comprehend that number, picture the entire weight of the Earth's atmosphere, every molecule of air, from the ground beneath your feet to the edge of space, pressing down on a single square inch. Now multiply that sensation by 250 billion. This is the crushing, perpetual force that exists at the solar core, a pressure so immense that it overcomes the most powerful repulsive forces in nature. This unimaginable pressure is the direct and unavoidable consequence of gravity's relentless pull. The entire mass of the Sun, which is 330,000 times the mass of our entire planet, is constantly collapsing inward, drawn toward its own center by its overwhelming self-gravity. Yet the Sun does not simply shrink to a point. This inward crush is met by an equally powerful outward push from the intense heat and pressure generated within the core itself. It is this perfect dynamic balance, a state known as hydrostatic equilibrium, that allows a star to maintain its stable size for billions of years. The inward pull of gravity is perfectly counteracted by the outward push of thermal pressure. Without this crushing gravitational force, the core would simply expand and cool, and the star's vital engine would sputter and die. It is this very pressure that creates the conditions for the universe's most fundamental power source, nuclear fusion. Deep within this pressurized crucible, hydrogen nuclei, which are single protons, are squeezed together with such phenomenal force that they overcome their natural electromagnetic repulsion. Remember, like charges repel each other and protons are all positively charged. Under normal conditions, they would never get close enough to interact. But under the star-crushing pressure of the solar core, they are forced into proximity so intimate that another, much stronger force can take over, the strong nuclear force. This is the glue that binds the universe at its most fundamental level, and it only acts over incredibly short distances. When the pressure forces protons close enough for this powerful force to engage, they can fuse, setting off a chain reaction that transforms the fundamental building blocks of matter. In a multi-step process known as the proton-proton chain, 4 hydrogen nuclei are fused together to create a single nucleus of helium. But here is the true magic of this alchemy. The resulting helium nucleus has slightly less mass than the 4 protons that created it. That tiny bit of missing mass has not vanished. It has been transformed directly into pure energy in accordance with Einstein's most famous equation. This is the secret of starlight. Every photon of light that travels across the vacuum of space to warm our planet, every ray of sunshine that has ever fallen on Earth, began its existence as a tiny deficit of mass in the heart of a star, liberated by the unimaginable pressure at its core. The energy produced is staggering. In the Sun's core, 620 million metric tons of hydrogen are fused into 616 million metric tons of helium every single second. The missing 4 million tons of mass are converted directly into energy, an output equivalent to detonating over 100 billion 1 megaton nuclear bombs per second, continuously for billions of years. This is the furnace that has powered our solar system for 4.6 billion years, and it will continue to do so for billions more. This process of nuclear fusion, born from incomprehensible pressure, is what makes the universe a living, luminous place. It is the reason galaxies are visible across vast cosmic distances, and it is the ultimate source of the energy that drives nearly every process on Earth, from photosynthesis in plants to the weather in our atmosphere. The core of a star is a testament to the fact that from the most crushing forces imaginable, the universe can birth the very light that allows us to see and understand it, a brilliant and enduring fire sparked in a crucible of unimaginable force. But if you thought the fury of a star's core was immense, consider the sheer physical size that some stars can attain, swelling to such colossal proportions that they defy all sense of scale. We are leaving behind the compact power of stellar engines and entering the realm of the truly gigantic, the hypergiants. To understand these leviathans, let's take a journey to the constellation Canis Major, where we find a star that redefines the word star itself, VY Canis Majoris. This is not a star in the way we think of our own steady sun. It is a cosmic titan, a seething, unstable behemoth in the final, violent chapters of its life. To grasp its scale, let's perform a simple but staggering thought experiment. Imagine carefully removing our sun from the center of our solar system and replacing it with VY Canis Majoris. Our sun, for all its importance, is a mere speck in this comparison, with a diameter of about 864,000 miles. If VY Canis Majoris were centered where our sun is, its unimaginably vast outer atmosphere would not just swallow Mercury, Venus, Earth, and Mars. It would extend outward, engulfing the entire asteroid belt, and would keep going, swallowing the gas giant Jupiter itself. The surface of this star would lie beyond Jupiter's orbit, meaning every planet out to, and including Jupiter, would be orbiting deep within its incandescent, tenuous layers. The entire inner solar system would be inside the star, a concept so vast it challenges our ability to visualize space itself. This is not a dense, solid object, of course. It is a sphere of incredibly hot, thin plasma. But its physical size is so immense that light, traveling at 186,000 miles per second, would take more than 6 hours to travel from one side of the star to the other. A single commercial jet flying at its cruising speed would need over 1,100 years to circumnavigate this one star just once. This monumental size comes with a cost: instability. VY Canis Majoris is a pulsating variable star, meaning it rhythmically expands and contracts, growing brighter and dimmer over long periods. It is also shedding its own mass at a ferocious rate, casting off colossal clouds of gas and dust in immense eruptions. These are not gentle solar winds, they are titanic belches of stellar material, each one containing many times the mass of our entire planet. The star is quite literally tearing itself apart, its own radiation pressure proving too powerful for its waning gravity to contain. This process has enshrouded the star in a complex and beautiful nebula of its own making, a cosmic crime scene of ejected material that tells the story of its violent past. The fate of such a monster is as epic as its life. Stars of this size live fast and die young. While our sun will shine steadily for billions of years, a hypergiant like VY Canis Majoris burns through its nuclear fuel in just a few million. Its core becomes a layered onion of successively heavier elements: helium, carbon, neon, oxygen, and finally, a core of iron. And it is iron that is the star's death knell. Unlike previous elements, fusing iron does not release energy, it consumes it. The moment an iron core grows too large, the outward pressure from fusion vanishes instantly. With no support against its own immense gravity, the core collapses catastrophically in less than a second. The outer layers of the star, suddenly without a foundation, come crashing down at a significant fraction of the speed of light, only to rebound off the newly formed, impossibly dense neutron star or black hole at the center. The resulting shockwave rips through the star in one of the most energetic events since the Big Bang, a supernova. But for a hypergiant, even a normal supernova might not be the end. There is a growing class of stellar explosions that are thought to be the final acts of these most massive stars: hypernova and potentially pair instability supernova. In a hypernova, the collapse results in a supernova paired with a long-duration gamma-ray burst, a focused beam of the highest energy radiation in the universe, which can outshine an entire galaxy for a brief moment. In an even more extreme scenario, a pair instability supernova, the core becomes so hot that the energy itself begins to spontaneously create matter and antimatter pairs. This process robs the core of its supporting pressure, leading to a runaway collapse and a thermonuclear explosion so utterly complete that it obliterates the star entirely. Leaving no remnant behind, the star is utterly vaporized, scattering its enriched guts across the galaxy. The existence of hypergiants like VY Canis Majoris is therefore a crucial part of the cosmic cycle. Their short, brilliant lives and their spectacular, mass-shedding deaths are the primary forges for the heavy elements that make up our world. The oxygen we breathe, the silicon in the rocks beneath our feet, and the iron in our blood were all forged in the hearts of massive stars and scattered across the galaxy in their final, glorious supernova explosions. So when we look at a star like this, we are not just looking at a point of light. We are witnessing a cosmic factory, a temporary, unstable, and breathtakingly vast engine that manufactures the very elements of life itself before going out in a blaze of glory that seeds the universe for generations to come. Yet for all the violence of stellar explosions and the lonely wanderings of rogue planets, one of the most profound and enduring forms of cosmic chaos occurs on the grandest scale of all: the collision and consumption of entire galaxies. We often picture galaxies as majestic, stable islands of stars, drifting in serene isolation through the void, but the reality is far more dynamic and brutal. Galaxies are social structures often found in clusters and groups, and in these dense cosmic neighborhoods, gravitational encounters are inevitable. This leads to a process of galactic cannibalism, where larger, dominant galaxies gravitationally tear apart and absorb their smaller neighbors, a sequence of events that fundamentally reshapes the participants and drives the evolution of the universe's largest structures. To understand this, we must first abandon the idea of galaxies as solid objects. A galaxy is mostly empty space, a vast collection of stars, gas, and dark matter held together by gravity. When two galaxies pass close to one another, their individual stars rarely, if ever, physically collide. The distances between them are far too great. Instead, it is their immense gravitational fields that interact, weaving a complex and destructive dance. As the galaxies swing past each other, their gravitational pull acts like a cosmic tidal force. Just as the Moon's gravity stretches Earth's oceans, the gravity of one galaxy violently tugs on the stars and gas of the other. This can rip long, streaming tails of stars out into intergalactic space, creating magnificent but tragic bridges and loops that can stretch for hundreds of thousands of light years. These tidal tails are the first visible sign of a galactic merger in progress, beautiful scars etched across the sky by gravity's relentless pull. For a smaller galaxy, this close encounter is often a death sentence. If it passes too close to a larger companion, it can be completely disrupted. Its stars are stripped away and scattered, becoming part of the larger galaxy's halo, a diffuse cloud of stars that surrounds the main galactic disk. Its gas clouds are compressed and shocked, collapsing to ignite furious bursts of new star formation. The most dramatic example of this in our own cosmic backyard is the ongoing cannibalization of the Sagittarius dwarf elliptical galaxy by our own Milky Way. This tiny satellite galaxy has been orbiting our own for billions of years, and with each pass, the Milky Way's gravity pulls it apart, stealing its stars and weaving them into a vast, faint stream that encircles our entire galaxy. We are quite literally in the process of consuming a neighbor, a slow-motion act of cosmic ingestion that will eventually see the Sagittarius dwarf completely dissolved, its identity erased as its stars become just another part of the Milky Way's extensive history. But galactic cannibalism is not limited to giants consuming dwarves. Sometimes two galaxies of roughly equal size will meet, leading to a more symmetrical and spectacular collision. When two spiral galaxies of similar mass merge, the process is one of the most transformative events in the universe. Their delicate spiral structures are the first things to be destroyed, shredded by gravitational forces into a chaotic, tangled mess. The galaxies will swing past each other several times, their gravitational interaction pulling them into an ever-tightening embrace. During this chaotic period, the compression of their vast clouds of hydrogen gas triggers an incredible firestorm of star birth known as a starburst. In a starburst galaxy, the rate of star formation can be hundreds or even thousands of times greater than in a normal galaxy like the Milky Way. The most famous result of such a merger is an elliptical galaxy. While spiral galaxies are thin, ordered disks, ellipticals are featureless, football-shaped swarms of stars. For a long time, astronomers wondered how these structureless giants formed. The leading theory is that they are the end products of major galactic mergers. As two spirals merge, their stars, which were orbiting in an orderly disk, are thrown into random, chaotic orbits. The resulting object no longer has a defined plane of rotation. It becomes a bloated, spherical collection of stars. The gas that isn't used up in the starburst is either blown away by powerful stellar winds from the new supernova or funneled directly toward the center, where it can feed and awaken the supermassive black holes that lurk in both galaxies. This leads to another dramatic consequence, the ignition of quasars. The influx of fresh gas onto the central black holes can turn them into brilliant active galactic nuclei, whose radiation can outshine the entire rest of the merging galaxy. This powerful feedback can then regulate the final stages of the merger, blowing away any remaining gas and effectively halting star formation, leaving behind a red and dead elliptical galaxy, populated mostly by old red stars. This entire cycle, from serene spiral to violent starburst to quiescent elliptical, is a key driver of galactic evolution. Our own Milky Way is on a collision course with the nearby Andromeda galaxy, and in about 4 billion years, the two spirals will begin a billion-year dance that will ultimately merge them into a single, large elliptical galaxy, which astronomers have whimsically named Milkdromeda. This future event will trigger a spectacular but final burst of star formation, fundamentally altering the night sky for any potential future inhabitants of our solar system. Galactic cannibalism, therefore, is not mere destruction, it is a creative force. It builds the largest galaxies in the universe, it forges new generations of stars from the wreckage of the old, and it shapes the diverse population of galaxies we see today. It is the universe's way of recycling on the grandest possible scale, a slow gravitational ballet where entire islands of stars are torn apart and remade, proving that even the mightiest structures in the cosmos are subject to change and that from celestial violence new forms of order can emerge. Now, as we contemplate the immense gravitational dances that shape entire galaxies, we must confront one of the most profound and puzzling realities in all of modern cosmology, the fact that the vast majority of the matter holding these cosmic structures together is completely invisible to us. This brings us to the enigmatic presence of dark matter halos. Picture a majestic spiral galaxy like our own Milky Way, with its brilliant central bulge and sweeping arms of stars. What you are seeing in any telescope image is only a tiny fraction of the galaxy's true substance. The stars and glowing gas we observe are merely the visible inhabitants of a much larger, unseen metropolis. Enveloping the entire galaxy is an immense, roughly spherical halo of a mysterious substance known as dark matter. This halo is colossal, stretching far beyond the visible edge of the galaxy, and it contains over 5 times more mass than all the ordinary matter, the stars, planets, and gas combined. It is this invisible dark matter halo that acts as the galaxy's primary gravitational skeleton, providing the framework upon which the luminous galaxy is built. Without this unseen anchor, galaxies like our own would simply fly apart. The stars in the outer regions of spiral galaxies orbit at speeds that defy the predictions based on visible matter alone. If a galaxy's mass were concentrated only in its bright center, stars and gas clouds farther out should orbit much more slowly, just as Pluto moves more sluggishly around the Sun than Mercury does. But observations tell a very different story. The orbital speeds of these outer stars remain high, almost constant, regardless of their distance from the galactic center. The only plausible explanation is that they are being whipped around by the gravitational pull of a huge amount of mass that we cannot see, mass distributed throughout the vast dark halo that envelops the entire visible galaxy. So, what exactly is this mysterious substance? We call it dark matter because it does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is utterly transparent. It doesn't interact with light at all, which is why our telescopes, from radio to gamma ray, are blind to it. We only know it's there because of its gravitational influence on the things we can see. We can map its distribution by observing how its gravity bends the light from more distant galaxies, an effect called gravitational lensing, and by studying the motion of stars and gas within galaxies. The leading theory is that dark matter is made of some kind of exotic, undiscovered particle that rarely, if ever, interacts with normal matter through any force other than gravity. It's not made of atoms, it's not the black holes of dead stars. It's something entirely new, a fundamental component of the universe that has so far eluded all our attempts at direct detection. This means the cosmos we see is just the shimmering froth on a deep, dark ocean of unknown material, a hidden architecture that dictates the large-scale structure of everything. The very existence of dark matter halos forces us to accept a humbling truth. Most of the universe is made of something we do not yet understand, a silent, invisible presence that has shaped the destiny of galaxies from the very beginning of time. But to truly appreciate the immense structure of a single galaxy's dark matter halo, we must pull our perspective back even farther, to a scale so vast it encompasses the entire observable universe. This brings us to the grandest pattern in all of existence, the cosmic web. Forget the idea of galaxies being randomly scattered like glitter thrown into the darkness. The universe is in fact meticulously structured. On the largest scales, matter is arranged in a breathtakingly complex architecture that resembles a colossal spider's web, a network of unimaginable proportions. This web consists of three primary components: dense knots where thousands of galaxies swarm together in massive clusters, long, thin filaments that stretch across millions of light-years like cosmic highways, and vast, empty voids between them, immense, spherical deserts of near-nothingness that can span hundreds of millions of light-years. This isn't a small pattern. This is the underlying skeleton of the cosmos itself, the fundamental organization of all visible matter. And the astonishing truth is that this entire monumental structure is built upon a framework of the invisible. The cosmic web is first and foremost a web of dark matter. In the early universe, slight fluctuations in the density of dark matter, amplified by the force of gravity over billions of years, acted as the seeds for this entire architecture. Regions that were slightly denser than average pulled in more dark matter, growing even denser, while less dense regions were drained of it. This process created a gravitational landscape of hills and valleys on a cosmic scale. The ordinary matter, the hydrogen and helium gas that would eventually form stars and galaxies, simply followed this gravitational blueprint. The gas flowed along the gravitational contours of the dark matter, falling into the filaments and gathering at the intersections where the pull was strongest. This is why we see galaxies strung along these filaments like pearls on a string and crowded into massive clusters at the nodes where multiple filaments meet. The voids, then, are the regions largely emptied of both dark and ordinary matter, the gravitational low points in the universe. The scale of this structure is almost impossible to internalize. A single filament in the cosmic web can be hundreds of millions of light-years long, yet only a few million light-years in diameter. To travel from one end of a major filament to the other at the speed of light would take longer than the entire history of life on our planet. And the voids are even more staggering. The Boötes void, one of the largest known, is so enormous that if our Milky Way were at its center, we would not have discovered that other galaxies even existed until the 1920s. We would have believed our galaxy was the entire universe floating in a perfect, empty darkness. This intricate web is not static, it is a dynamic, evolving system. Over cosmic time, gravity continues to pull matter along the filaments toward the dense clusters. This process, known as cosmic accretion, is how galaxy clusters grow to such immense sizes, cannibalizing smaller groups of galaxies that flow in along these dark matter highways. The web itself is also evolving, with filaments thinning and stretching as the universe expands, and the voids growing ever larger and emptier. Mapping this cosmic web has been one of the great achievements of modern cosmology. Astronomers use massive surveys to plot the three-dimensional positions of millions of galaxies, and when they do, this vast cell-like structure emerges from the data. It is a pattern predicted by our theories of the Big Bang and dark matter, and its observational confirmation stands as one of the strongest pieces of evidence we have for the existence of this mysterious substance. The cosmic web, therefore, is the ultimate expression of gravity's slow, relentless work. It shows us that the universe is not chaotic, but possesses a deep and beautiful order, a structure woven from the invisible fabric of dark matter and illuminated by the brilliant, shining knots of galaxies that trace out its form. It is the largest single pattern we have ever identified, a testament to the simple, powerful laws of physics operating across nearly 14 billion years of cosmic history. And yet, even the brilliant, starlit tapestry of the cosmic web and the silent dominance of dark matter cannot compare to the raw, luminous fury of a single point of light that can outshine it all. We now arrive at one of the most energetic and enduring mysteries in all of astronomy, the quasar. Discovered in the early 1960s, these objects appeared as star-like points of radio emission, hence the name quasi-stellar radio source. But their true nature was far more extraordinary. When astronomers managed to measure their distances, they were stunned. Quasars were not nearby stars, they were incredibly far away, their light having traveled for billions of years to reach us. This presented an immediate and profound paradox. How could something so distant appear so bright in our telescopes? The answer, we now know, lies in a cosmic engine of almost unimaginable efficiency and power, an engine that resides at the very heart of an active galaxy. A quasar is the intensely luminous core of a galaxy where a supermassive black hole is in an extremely voracious feeding phase. But this is not the quiet, dark predator we often imagine. This is a black hole caught in the act of a celestial feast, and the brilliance of the quasar is the light from its table. The process begins with fuel. Enormous quantities of gas, dust, and even entire stars are drawn inexorably toward the black hole's event horizon by its overwhelming gravity. But this material doesn't simply vanish. Conservation of angular momentum ensures it cannot fall directly in. Instead, it forms a vast, flattened, swirling vortex around the black hole known as an accretion disk. Picture a whirlpool of fire on a scale that could engulf our entire solar system, a maelstrom where particles race at velocities approaching a significant fraction of the speed of light. The inner regions of this disk orbit furiously fast, while the outer regions move more slowly, and the resulting friction between these layers, combined with the influence of powerful magnetic fields, heats the gas to staggering temperatures of millions of degrees. At such extremes, the matter doesn't just glow with visible light. It shines with an intense, blazing fury of ultraviolet and X-ray radiation, turning the entire disk into a lighthouse beacon of high-energy photons. The sheer amount of energy released in this process defies belief. While nuclear fusion in a star's core is remarkably efficient, converting about 0.7% of mass into energy, the process within a black hole's accretion disk is dozens of times more effective. As matter loses gravitational potential energy on its final, frantic plunge toward the event horizon, a tremendous fraction of its mass is transformed directly into pure radiation according to Einstein's famous equation. This is the secret of the quasar's incredible luminosity. A single, typical quasar can outshine an entire galaxy containing hundreds of billions of stars, and it does so from a region not much larger than our own solar system. This concentration of power is so intense that the radiation pressure from the light itself creates a dynamic balance, actively pushing outward on the infalling material and regulating the black hole's meal. The light from these cosmic beacons is so piercing that we can detect them from the farthest reaches of the observable universe, allowing us to look back in time to an era when such voracious black holes were far more common. In fact, the most distant quasars we see are windows into the universe's infancy, showing us a time when galaxies were young and their central black holes were gorging on the abundant gas around them. But the spectacle doesn't end with the brilliant disk. Often, the black hole's immense spin and its powerful magnetic fields act like a cosmic particle accelerator. channeling some of the infalling material into two narrow, perpendicular jets that blast away from the poles of the accretion disk at nearly the speed of light. These jets, composed of energetic plasma, can stretch for hundreds of thousands of light years, far beyond the confines of the host galaxy itself, punching into intergalactic space. When one of these relativistic jets is fortuitously aimed almost directly at Earth, we see an even more extreme and variable type of object known as a blazar, whose intense emission can fluctuate wildly over periods as short as hours, signaling violent storms happening in the immediate vicinity of the black hole. The presence of a brilliant quasar has a profound and transformative effect on its entire host galaxy, a relationship known as feedback. The incredible outpouring of energy and the powerful jets can blow away the vast reservoirs of gas needed to form new stars, effectively shutting down star formation and leaving the galaxy to evolve into a red and dead elliptical. In this way, the quasar at a galaxy's heart, though relatively brief in cosmic terms, can dictate the long-term fate of its entire stellar population, a testament to the power of a single, focused point of energy to shape a cosmos. But the immense gravitational pull that powers these brilliant quasars and tears stars apart also has a far more subtle and mind-bending effect, one that strikes at the very heart of our experience of reality, the passage of time itself. This brings us to one of the most incredible predictions of Einstein's theory of general relativity, a phenomenon that sounds like pure science fiction but is a verified fact of our universe. Near a black hole or any incredibly massive object, time does not flow at the same rate as it does elsewhere. Gravity, according to Einstein, is not just a force that pulls on objects, it is a curvature in the very fabric of spacetime. Imagine spacetime as a vast, flexible rubber sheet. A massive object like a star or a black hole creates a deep well in this sheet. Now picture time as a tiny ball rolling across this sheet. As the ball rolls closer to the deep well, its path, its experience of time, is stretched and slowed down. This is the essence of gravitational time dilation. For an observer brave or unfortunate enough to venture close to a black hole's event horizon, time would appear to pass perfectly normally. Their watch would tick second by second, and their biological processes would continue at their usual pace. However, if they could look outwards and communicate with a colleague stationed on a spaceship far from the black hole's influence, a staggering disconnect would emerge. They would see their colleague's actions speed up as if watching a video on fast forward. Their colleague's voice over the radio would become a high-pitched, rapid-fire chipmunk squeak. Meanwhile, from the perspective of the colleague safely far away, the opposite would be true. They would see their adventurer friend moving in agonizingly slow motion, their every gesture stretched over hours or days. Their radio transmissions would be drawn out into a deep, low-frequency drone with seconds between each syllable. The closer the adventurer gets to the event horizon, the more extreme this effect becomes. From the distant colleague's viewpoint, time for their friend would slow to an absolute crawl, approaching a full stop at the very threshold of the event horizon. It would appear to take an infinite amount of time for the adventurer to actually cross that boundary, their image frozen and red shifted into oblivion. The mechanism behind this is the incredible gravitational potential at the black hole's edge. The laws of physics demand that the speed of light in a vacuum is constant for all observers. For this to hold true in a powerful gravitational field, something else has to give, and that something is time itself. Time stretches and slows down to ensure that light, even when climbing out of a deep gravitational well, maintains its constant speed. This isn't just a theoretical curiosity. We measure this effect every single day. The global positioning system, or GPS, that guides our cars and phones would be useless without accounting for time dilation. The satellites in orbit are in a slightly weaker gravitational field than we are on Earth's surface, which means their atomic clocks run faster by about 45 millionths of a second per day. If this tiny difference weren't constantly corrected, the GPS system would accumulate errors of several miles within just a few hours, rendering it completely inaccurate. So this bizarre consequence of extreme gravity is not only real, it's a practical necessity for modern technology. In the context of a black hole, this effect becomes the ultimate one-way journey. An astronaut falling into a black hole would, from their own perspective, cross the event horizon in a finite amount of time. But from the viewpoint of the entire outside universe, their final approach would be stretched across the eons. They would become a living fossil, a snapshot of a moment, as the cosmos around them ages billions of years. They could, in theory, witness the entire future history of the universe unfold before them in a final, fleeting instant before their own destruction, a solitary spectator to the ultimate fate of all things, all because of the profound warping of time by an unforgiving gravity. And yet, even as we contemplate the warping of time itself, our planet is continuously bombarded by a silent, invisible rain of atomic shrapnel from the most violent events in the cosmos. We exist under a constant, gentle drizzle of high-energy particles known as cosmic rays, a form of radiation that is both a testament to the universe's incredible power and a significant challenge for our future among the stars. Despite their name, cosmic rays are not rays of light at all. They are actually subatomic particles, mostly single protons, the nuclei of hydrogen atoms, but also the nuclei of heavier elements like helium, carbon, and even iron, all accelerated to velocities that are a breathtaking fraction of the speed of light. They carry a staggering amount of energy for their minuscule size, with some of the most energetic particles, whimsically named "Oh my God" particles, possessing the kinetic energy of a professionally thrown baseball, all packed into a single, invisible proton. The origin of these cosmic bullets is a story written in celestial violence. The majority of the lower energy cosmic rays that constantly pepper our atmosphere are thought to be accelerated by the colossal shockwaves of supernova explosions. When a massive star dies, it blasts its outer layers into space at thousands of kilometers per second. This creates a rapidly expanding shell of gas and a powerful shock front that moves through the interstellar medium. Charged particles like protons can become trapped by magnetic fields on either side of this shockwave. As the shock front rolls over them, they are reflected back and forth, gaining a little more energy with each crossing, like a tennis ball being volleyed between two approaching rackets. After thousands or even millions of these cycles, the particles are eventually flung out into the galaxy, ejected with enough energy to travel for millions of years. But the very highest energy cosmic rays, those truly enigmatic oh my God particles, demand an even more powerful engine. Their origins are still a subject of intense research, but the prime suspects are the most extreme objects we know of, the active cores of distant galaxies, where supermassive black holes are powering brilliant quasars and blasting out jets of plasma, or perhaps the cataclysmic mergers of neutron stars and black holes. These cosmic cannons can impart energies to a single particle that dwarf anything we can create in our most powerful particle accelerators here on Earth, like the Large Hadron Collider. The journey of these particles is a long and lonely one. They travel for millions of light years across the galaxy, their paths twisted and bent by the weak magnetic fields that permeate interstellar space. By the time they reach us, their direction is completely scrambled, making it nearly impossible to trace a single particle back to its specific source. It is like trying to find the origin of a single, specific raindrop in a downpour after it has been blown about by a turbulent wind for centuries. When one of these high-energy messengers finally encounters Earth, it doesn't reach the surface directly. It slams into the upper atmosphere, colliding with a molecule of nitrogen or oxygen with the force of a miniature bomb. This collision creates a spectacular but invisible cascade of secondary particles, a shower of pions, muons, electrons, and gamma rays that rains down over an area the size of a city block. It is this secondary shower that we can detect with instruments on the ground, the faint, scattered echo of a cosmic catastrophe that occurred light years away. For most of us on the surface, this cosmic rain is a mere curiosity. Our thick atmosphere and the planet's magnetic field act as a superb shield, absorbing the vast majority of these particles and protecting life below. But for astronauts and future space travelers, cosmic rays present a serious and persistent hazard. Outside the protective cocoon of Earth's atmosphere and magnetosphere, they are exposed to this continuous, penetrating radiation. These high-energy particles can slice straight through the hull of a spacecraft and the bodies of the astronauts inside. When a heavy atomic nucleus like that of iron tears through human tissue, it doesn't just cause simple damage like an X-ray might. It creates a microscopic but devastating path of ionization, shredding DNA molecules and killing cells. This constant, low-level exposure increases the lifetime risk of cancer, and there is also concern about its effects on the central nervous system, potentially impacting cognitive function and memory during long-duration missions to the Moon or Mars. Shielding against them is an immense engineering challenge. Lead or other heavy metals which work well for medical X-rays can actually make the problem worse with cosmic rays. When a high-energy particle slams into a dense atomic nucleus in the shield, it can shatter it, creating a secondary shower of even more particles inside the spacecraft. The most promising solutions involve innovative materials with high hydrogen content, like polyethylene or water tanks, which can slow the particles down more effectively through a series of smaller, less destructive collisions. The silent, omnipresent rain of cosmic rays is therefore a humbling reminder of our place in the cosmos. We live on a sheltered world in a violent neighborhood, and each of these invisible particles is a tiny courier, carrying with it the untamed energy of supernova, the fury of quasar jets, and the raw power of the most extreme engines the universe has to offer. But our journey through the solar system is not yet complete. We have spoken of planets and moons, of asteroids and the distant Kuiper belt, but to truly find the final frontier of our sun's gravitational dominion, we must voyage far beyond all of these into a realm of near-total darkness and unimaginable scale. This is the Oort cloud, the solar system's final, vast and silent frontier. Imagine a shell, a colossal spherical cloud surrounding our entire planetary system. Its inner edge is thought to begin roughly 2,000 times farther from the Sun than Neptune, and its outer edge stretches perhaps halfway to the very nearest star. To grasp that distance, consider the Voyager 1 spacecraft, which has been traveling away from Earth for over 40 years at 38,000 miles per hour. It would need another 300 years just to reach the Oort cloud's inner boundary, and then perhaps 30,000 more years to fly completely through it. This is not a place you can see or visit. It is a theoretical construct, a gravitational sphere of influence populated by trillions, perhaps even quadrillions, of icy objects left over from the solar system's violent birth. These are not compact planets or even large asteroids. They are primordial planetesimals, the very building blocks of the planets that never coalesced into a larger world. Each is a dirty snowball, a frozen relic composed of water ice, frozen gases like ammonia and methane, and a sprinkling of dust and rock, all orbiting the Sun in a profound and perpetual deep freeze where temperatures hover just a few degrees above absolute zero. In this eternal twilight, the Sun is not a disk of light, but merely the brightest star in a pitch-black sky, providing no warmth and casting no significant shadow. These icy bodies are so far apart that a traveler on one would likely not see its nearest neighbor, even with a powerful telescope. They are lonely islands in a sea of darkness, separated by distances of millions of miles. The existence of the Oort cloud is the only explanation that fits the behavior of long-period comets. These are the spectacular, unpredictable visitors that sweep into the inner solar system from every conceivable direction, not from the flat plane of the planets, but from all points in the sky. Their orbits are immensely long, taking thousands or even millions of years to complete. Astronomers realized that these comets must originate from a vast spherical reservoir surrounding the solar system, a place where their orbits can be stable for billions of years until a chance gravitational nudge sends one falling sunward. That nudge can come from the gentle cumulative pull of the Milky Way itself, or from a chance encounter with a passing star. Imagine the Oort cloud as a vast, loosely bound collection of icy particles, and every few million years, a star like our Sun's neighbors passes close enough to our system to act like a gravitational hand, stirring this cloud and sending a shower of these icy planetesimals on a long fall toward the inner solar system. As one of these distant denizens of the Oort cloud begins its epic journey inward, the Sun's weak gravity at that distance slowly but inexorably takes hold, pulling it into a plummeting dive. For millennia, it travels through the void unchanged, but as it finally approaches the warmth of the inner solar system, a transformation begins. The Sun's heat starts to vaporize the volatile ices on its surface, and what was once a dark, inert lump of ice and rock erupts into life. It grows a glowing coma, a vast, fuzzy atmosphere of gas and dust, and often sprouts two magnificent tails. One, the dust tail, glows with reflected sunlight, curving gently behind the comet's path. The other, the ion tail, is a straight, ethereal blue streamer of gas particles pushed directly away from the Sun by the solar wind. These comets are more than just beautiful spectacles, they are cosmic time capsules. Having spent nearly 5 billion years in the deep freeze of the Oort cloud, their ices are pristine, largely unaltered since the very formation of the solar system. When we analyze the light from a comet's coma, we are effectively performing a chemical analysis of the original material from which our planetary system was built. They carry the recipe of our origins frozen in time. The Oort cloud, therefore, is far more than just a distant reservoir of ice. It is the solar system's ultimate attic, storing the leftover raw materials from our construction. It is the source of some of the most breathtaking celestial events witnessed from Earth, and it acts as a gravitational border defining the true, mind-bogglingly vast extent of our Sun's kingdom. It is a silent, dark, and frigid realm, but it holds within its countless icy bodies the frozen memory of our own beginnings, a reminder that our vibrant, sun-warmed inner solar system is just the bright, central heart of a much larger, darker, and more ancient domain. In the silent, dark spaces between the stars and galaxies, light travels for billions of years on a perfectly straight path, or at least that's what we used to think. But Einstein's theory of general relativity revealed a far more malleable reality, predicting that gravity doesn't just pull on matter, it warps the very fabric of space and time, and as a consequence, it bends the path of light itself. While this effect is minuscule around stars like our Sun, there exists a natural phenomenon in the cosmos that takes this principle and scales it up to almost unbelievable proportions, turning entire clusters of galaxies into the universe's most powerful telescopes. This is the incredible power of gravitational lensing. Imagine a galaxy cluster, one of the most massive structures in the universe, containing thousands of galaxies, vast clouds of hot gas, and an immense halo of dark matter, all bound together by gravity. The combined mass of this cluster is so stupendous that it creates a profound dent in the cosmic rubber sheet of spacetime. Now, picture a distant, faint galaxy located directly behind this cluster from our viewpoint on Earth. As the light from this background galaxy journeys toward us, it enters this warped region of space. Instead of traveling in a straight line, the light follows the curvature, its path bent around the massive cluster. From our perspective, it's as if the galaxy cluster is a gigantic cosmic magnifying glass. This lensing effect can distort, magnify, and even multiply the image of the distant background object. We see this manifested in several breathtaking ways. The most dramatic is the creation of Einstein rings, where the light from the background galaxy is smeared into a perfect or nearly perfect circle of light around the foreground cluster. This occurs only when the Earth, the cluster, and the distant galaxy are in almost perfect alignment, a celestial bullseye that results in one of the most striking visual confirmations of Einstein's theory. More commonly, we see stretched and warped arcs of light, like celestial smiles curving around the cluster's center. These are not new objects, they are multiple, distorted images of the same single background galaxy. Its light bent and split into several paths around the gravitational well before all those paths finally converge at our telescopes. The practical application of this is nothing short of revolutionary for astronomy. Gravitational lenses act as natural telescopes, often referred to as nature's zoom lenses, allowing us to see galaxies that are otherwise far too distant and faint for our most powerful human-built observatories to detect. The cluster's gravity effectively amplifies the light from these incredibly remote objects, bringing the far reaches of the early universe into view. This has allowed astronomers to observe some of the first galaxies to form after the Big Bang, studying their shapes, sizes, and rates of star formation in unprecedented detail. But the utility of gravitational lensing extends far beyond just giving us a magnified view. It provides us with a direct and powerful method to weigh the galaxy cluster itself, including the one component we cannot see, dark matter. By carefully mapping the way the background light is distorted, astronomers can create a mass map of the foreground cluster. The degree of bending reveals the total mass present, and by subtracting the mass we can see in the form of stars and hot gas, we are left with a precise measurement of the invisible dark matter that makes up the bulk of the cluster's gravitational anchor. This technique has shown us that dark matter is not smoothly distributed, but is clumped together in a way that traces the overall structure of the cluster, confirming its role as the cosmic scaffolding upon which galaxies are built. Each lensing cluster becomes a unique natural experiment, a chance to probe the distribution of mass on a colossal scale and to test the fundamental laws of gravity across cosmic distances. The discovery and continued study of these gravitational lenses have fundamentally reshaped our understanding of the universe's architecture, providing both a window to its earliest epochs and a scale to weigh its most mysterious component, all through the subtle but undeniable warping of starlight by the sheer force of gravity. But if you thought a star's death was a final, singular event, think again. The end of a massive star in a supernova is not a conclusion, it is a dramatic new beginning. The explosion itself lasts only a moment, but its legacy is written across space for thousands of years in the form of a supernova remnant, an expanding shell of incandescent gas and shattered stellar material that continues to shape the galaxy long after the star itself is gone. Imagine a sphere of debris millions of degrees hot, racing outward from the point of detonation at speeds that can exceed 10,000 kilometers per second. A hypersonic shockwave of pure energy blasting into the cold, quiet gas of the interstellar medium. This is not a gentle expansion, it is the most powerful sustained mechanical force in the present-day universe. The leading edge of this shockwave is a wall of unimaginable violence. As it plows into the surrounding space, it heats the interstellar gas to temperatures so extreme that it glows fiercely across the entire electromagnetic spectrum, from radio waves to X-rays, creating the beautiful filamentary nebulae we see in telescope images, like the Veil Nebula or the Crab Nebula. These remnants are the primary foundries for many of the elements that make up our world. The supernova explosion itself forged the heaviest elements, from the oxygen we breathe to the iron in our blood, but it is the expanding remnant that performs the crucial act of cosmic recycling. It scoops up these newly minted atoms and hurls them far out into the galaxy, seeding vast regions of space with the raw materials for new planets and, ultimately, life. This process enriches the galactic ecosystem, ensuring that future generations of stars and planets form from dust that is laced with these essential heavy elements. Without this continuous enrichment cycle, the universe would be composed almost entirely of hydrogen and helium, and rocky, metal-rich worlds like Earth could never have formed. But the role of a supernova remnant goes beyond mere distribution. It is also a powerful catalyst for new creation. As the colossal shockwave expands, it does not move through a perfect vacuum. It encounters vast, frigid clouds of molecular gas and dust. The shock front rams into these clouds with the force of a celestial bulldozer, compressing them violently. This sudden, immense pressure can overcome the cloud's internal turbulence and its own weak gravity, triggering a chain reaction of collapse within the cloud. Dense knots form, and within these knots, the pull of gravity becomes strong enough to ignite the fusion furnaces of new stars. In this way, the death of one star can directly lead to the birth of dozens or even hundreds of new ones, a stellar generation born from the ashes of its predecessor. This feedback loop is a fundamental driver of galactic evolution. The most massive of these new stars will, in their turn, live short, brilliant lives and explode as supernovae themselves, creating new remnants that will again enrich and compress the interstellar medium, perpetuating the cycle. We see this beautifully illustrated in regions like the Cygnus Loop or the W50 supernova remnant, where the delicate, bubble-like structures we observe are actively interacting with nearby dark nebulae, triggering waves of star formation along their rims. The energy involved in this process is almost beyond calculation. A single supernova remnant can remain hot and expand for tens of thousands of years, its shockwave gradually slowing as it sweeps up more and more material, eventually dissipating its energy and merging back into the general interstellar medium. During its long life, it acts as a giant particle accelerator, its turbulent magnetic fields trapping cosmic rays and boosting them to incredible energies. The Crab Nebula, for instance, is not just a cloud of gas. It is a powerful source of high-energy particles and radiation, powered by the rapidly spinning neutron star or pulsar at its heart. This continuous injection of energy and matter keeps the galaxy in a state of dynamic chemical and physical change. So when we gaze at the intricate, glowing tapestry of a supernova remnant, we are not just looking at a ghost. We are witnessing a cosmic engine of destruction and creation, a furious, expanding bubble that is both a gravestone for a dead star and a nursery for the stars of tomorrow. It is a permanent reminder that in the grand economy of the cosmos, nothing is truly wasted, and that from the most violent ends can come the most essential and beautiful new beginnings. The universe is filled with spinning objects from planets to entire galaxies, but few can match the mind-bending precision and regularity of a cosmic metronome born from stellar catastrophe. We now turn our attention to a specific type of neutron star that takes its already extreme nature and adds a layer of rhythmic perfection, the pulsar. When a massive star goes supernova, the collapsed core that remains can, under the right conditions, become more than just a dense sphere of neutrons. It can transform into a celestial lighthouse, broadcasting its presence across the galaxy with a pulse so reliable it rivals the most accurate atomic clocks on Earth. The secret to this phenomenon lies in a powerful combination of rapid rotation and an intensely concentrated magnetic field. As the massive progenitor star collapses, a fundamental law of physics comes into play, the conservation of angular momentum. Just as an ice skater spins faster when they pull their arms in, the star's core, which was already rotating, spins up to an incredible velocity during its collapse. A typical pulsar can complete multiple full rotations every single second, with some, known as millisecond pulsars, spinning hundreds of times per second. At the same time, the star's original magnetic field is compressed and intensified, becoming trillions of times stronger than Earth's field. This magnetic field is not aligned with the star's axis of rotation, it is tilted. At the two magnetic poles of this rapidly spinning neutron star, intense beams of radiation are generated, focused by the magnetic field. These beams are not visible light. They are typically concentrated streams of radio waves, though some pulsars also beam out X-rays or gamma rays. Now imagine this cosmic cannon spinning at a dizzying rate, its twin beams sweeping through space like the light from a lighthouse on a dark, stormy coast. If the Earth happens to lie in the path of one of these sweeping beams, we detect a pulse of radiation each time it points in our direction. With every rotation, we get a flash, a pulse, and then silence as the beam swings away. This is the heartbeat of a pulsar, a tick-tock of cosmic energy that can be detected with radio telescopes. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was a moment of both shock and bewilderment. The signal was so perfectly regular, ticking with a period of about 1.3 seconds, that it was briefly and half-seriously nicknamed LGM-1 for Little Green Men, as it seemed to defy any known natural explanation. We now know these are not signals from an alien civilization, but the natural signatures of these spinning neutron stars. The precision of these pulses is what makes pulsars truly extraordinary tools for astronomy. Because a pulsar's spin is incredibly stable, the timing of its pulses can be predicted with phenomenal accuracy. Any tiny deviation in the expected arrival time of a pulse is not an error, it is a clue, a piece of data carrying information about the pulsar's environment. For instance, if a pulsar is in a binary orbit with another star, the pulses will arrive slightly early or late as the pulsar moves toward or away from us in its orbit. By meticulously tracking these timing variations, astronomers can measure the properties of the binary system with incredible precision, calculating the masses of the stars involved and even testing the predictions of Einstein's theory of general relativity. The first indirect evidence for gravitational waves came from observing the orbital decay of a binary pulsar system, a discovery that earned a Nobel Prize. This utility extends far beyond studying individual star systems. The incredible regularity of pulsar signals opens up the possibility of using them as a galactic navigation system. Imagine a future where spacecraft traveling between the stars could triangulate their position by comparing the arrival times of pulses from a network of known millisecond pulsars scattered across the galaxy. This pulsar positioning system would act as a cosmic GPS, providing a universal reference frame for navigation anywhere in the Milky Way. Furthermore, astronomers are attempting to use pulsars to detect gravitational waves directly on a galactic scale. By monitoring an array of the most stable millisecond pulsars across the sky, a project known as a pulsar timing array looks for correlated minute disturbances in their pulse arrival times. The hypothesis is that a passing, low-frequency gravitational wave from a colossal event, like the merger of two supermassive black holes, would slightly warp the spacetime between us and the pulsars, making the pulses arrive a little early or late in a specific, correlated pattern across the entire array. This ambitious endeavor is like turning the entire galaxy into a gravitational wave observatory, using these natural cosmic clocks to listen for the faintest ripples in the fabric of spacetime itself. So, while a pulsar is born from one of the most violent events in the universe, its legacy is one of profound order and utility. It is a beacon that not only illuminates the nature of matter under extreme conditions, but also serves as a precise tool for probing the dynamics of binary systems, a potential guide for interstellar travel, and a delicate instrument for sensing the subtle warp and weft of the cosmos. From the solitary beacons of pulsars and the silent expanse of the Oort cloud, we now journey to a world that feels like it was lifted straight from the realm of science fiction. Imagine standing on the surface of a planet where the sky is dominated not by one, but by two suns, a permanent binary sunset that would make any Star Wars fan feel right at home. This is Kepler-16b, the first confirmed unambiguous planet orbiting a pair of stars, a celestial body known as a circumbinary planet that proves such double sun systems are not just fantasy, but a vibrant reality in our galaxy. The two stars at the heart of this system are a fascinating pair themselves. The primary star, Kepler-16a, is a smaller, cooler orange dwarf star about 69% the mass of our Sun. Its companion, Kepler-16b, is a diminutive red dwarf, a mere 20% of our Sun's mass. These two stars are locked in a tight, mutual dance, orbiting each other about once every 41 days. Their gravitational relationship is so intimate that from the perspective of a distant observer, they would appear almost as a single, flickering point of light. It is around this dancing duo that the planet Kepler-16b makes its home, tracing a wide, stable orbit that encompasses both stars. The orbital dynamics of this system are a delicate and beautiful ballet, governed by the competing gravitational pulls of the two central stars. For a planet to have a stable orbit in a binary system, it must be far enough away that the gravitational tugs from the two stars average out into a single combined pull. If it ventured too close, the competing gravitational influences would quickly make its orbit unstable, flinging it out of the system or sending it crashing into one of the stars. Kepler-16b occupies this Goldilocks zone for stability, orbiting at a distance of about 65 million miles, similar to Venus's orbit in our own solar system, completing one full circuit around both stars every 229 days. This creates a fascinating and complex celestial calendar. Because the two stars are themselves moving, the planet experiences a constantly shifting gravitational landscape and a pattern of daylight and warmth that is unlike anything in our single-star system. But the true spectacle, the moment that would define life on this world, would be the sunset. Picture the two suns, one larger and orange, the other smaller and a deep, ruddy red, hanging together in the sky. As the planet rotates and the horizon begins to rise, the two stars would start their descent. Their different sizes and colors would create a breathtaking display. First, the larger orange star might begin to dip below the horizon, casting long, deep amber shadows. Then, as it disappears, the smaller red dwarf would remain in the sky for a while longer, bathing the landscape in a dim, crimson twilight. Finally, it too would sink below the horizon, plunging the world into a night that would be, for a time, truly dark. There would also be periods where the stars eclipse each other from the planet's perspective, a daily celestial event where one star passes in front of the other, causing a sudden, dramatic dip in brightness that would be a normal part of the daily cycle. While the visual spectacle is undoubtedly stunning, the conditions on Kepler-16b itself are far from hospitable. It is a cold, gas giant world, likely similar in composition to Saturn, with a mass about a third of Jupiter's. Its orbit places it just outside the system's habitable zone, the region where liquid water could exist on a rocky surface. With an estimated surface temperature of around -100 degrees Fahrenheit, it is a frigid world, its thick atmosphere probably a swirling mix of hydrogen, helium, and other gases, with no solid surface to stand on and witness those magnificent double sunsets. The very existence of Kepler-16b was a monumental discovery that shattered old assumptions. For a long time, astronomers questioned whether stable planetary orbits were even possible in the chaotic gravitational environment of a binary star system. The discovery of this world, made by NASA's Kepler telescope using the transit method, proved definitively that planets can and do form in these complex systems. The Kepler telescope detected the planet by noticing the tiny, regular dimming of the binary star's combined light, not just from the planet passing in front of one star, but from it passing in front of both, and even from the stars eclipsing each other. This intricate light curve provided a wealth of data, allowing scientists to pin down the sizes, masses, and orbits of all three bodies with remarkable precision. This single discovery opened up an entirely new class of planetary systems for exploration. Since Kepler-16b, numerous other circumbinary planets have been found, some even within their system's habitable zone, raising the tantalizing possibility of a rocky world with liquid water orbiting two suns. The confirmation of these Tatooine-like worlds dramatically expands the potential real estate for planets in our galaxy, suggesting that binary star systems, which make up about half of all star systems, are not wastelands for planet formation, but can be vibrant, complex homes for worlds of their own, each with a sky that tells a story of gravitational harmony written in light and shadow. But just when we thought we had our solar system neatly categorized, a small, distant world delivered a stunning surprise that forced us to rewrite the textbooks on planetary geology. Our next stop takes us to the frigid, dark frontier of the Kuiper Belt, to a world that, until very recently, was little more than a blurry pixel in our largest telescope's Pluto. When the New Horizons spacecraft flew past this dwarf planet in 2015, it shattered our expectations, revealing a world of breathtaking complexity, a landscape not of a dead, frozen relic, but of a surprisingly active and dynamic body. Among its many wonders, ice mountains, vast glaciers of nitrogen ice, and possible cryovolcanoes, one of the most unexpected discoveries was the presence of vast, wind-sculpted dunes. The very idea of dunes on Pluto seems at first to defy logic. Dunes, like those in the Sahara Desert on Earth or in the vast sand seas of Mars, require two key ingredients: a supply of loose, granular material and an atmosphere with enough density to lift and transport those grains. Pluto, with its surface temperature of -387 degrees Fahrenheit and an atmospheric pressure 100,000 times thinner than Earth's, seemed like the last place you would find such a phenomenon. Its atmosphere is a wispy, transient envelope of nitrogen with traces of methane and carbon monoxide, and for decades it was assumed to be far too thin to have any significant effect on the surface. Yet there they were, captured in stunning detail by New Horizons, extensive fields of ripples and dunes stretching across the border of a massive, heart-shaped nitrogen ice plain known as Sputnik Planitia. These aren't dunes of sand, of course, but of something far more exotic, tiny grains of methane ice. The discovery immediately presented a fascinating planetary puzzle. How could winds in such a negligible atmosphere possibly move these frozen particles? The answer lies in a delicate and surprising combination of Pluto's unique conditions. First, the source of the dune material itself is critical. The dunes are situated near a major mountain range made of water ice, which on Pluto is as hard as bedrock. Scientists theorize that patches of methane ice on the sun-facing slopes of these mountains are being sublimated, turning directly from a solid into a gas in Pluto's weak sunlight. This process releases tiny, sand-like grains of methane ice into the extremely thin air, but the atmosphere is still far too thin for simple wind to pick them up as it would on Earth or Mars. This is where Pluto's second secret comes into play, its unusual atmospheric circulation. Despite the low pressure, the vast, smooth expanse of Sputnik Planitia plays a crucial role. This glacier of frozen nitrogen undergoes a slow, convective churning over geological timescales. As the sun warms the nitrogen ice, some of it sublimates, adding gas to the atmosphere. The surrounding topography and the weak sunlight create gentle but persistent breezes. Crucially, calculations show that the winds needed to transport the methane grains are just at the threshold of what Pluto's atmosphere can produce. The methane grains are also incredibly light and small, making them easier to lift than denser sand would be. The process is not a constant, raging sandstorm, but a slow, almost imperceptible creep of material, grain by grain, over thousands of years. The very existence of these dunes tells a profound story of planetary activity. It proves that Pluto, despite its small size and immense distance from the Sun, is not a static, frozen billiard ball. It possesses a complex and interacting system where its solid surface, its thin but dynamic atmosphere, and even its weak sunlight all work together to sculpt and reshape the landscape. The methane dunes are a testament to the tenacity of geological processes, showing that even in the most marginal of environments with the most unlikely of ingredients, nature finds a way to create familiar landforms through alien means. They stand as a permanent reminder that our solar system is full of active, evolving worlds in the most unexpected places, and that the definition of a living planet is far broader and more wonderful than we ever imagined. But if you want to find truly surprising water in the solar system, you don't always need to look for vast hidden oceans. Sometimes the most tantalizing clues are written right on the surface, in fleeting, seasonal stains that hint at a world that may not be as bone-dry as it appears. Our journey now takes us back to the familiar, rusty landscapes of Mars, a world we've long considered a desiccated desert. Yet, high-resolution images from orbiting spacecraft have revealed a mysterious and compelling phenomenon that seems to defy this arid reputation. Streaking down the steep, sun-facing slopes of crater walls and canyon cliffs are narrow, dark lines that appear, lengthen, and then fade with the Martian seasons. These are the recurring slope lineae, or RSLS, and they are one of the most debated and exciting discoveries in modern Martian science. The pattern is remarkably consistent. As the Martian spring and summer warm the slopes, these dark streaks begin to form at a point higher up and then seem to flow downhill, sometimes for hundreds of meters, before they eventually fade and disappear as the colder temperatures of autumn and winter return. Their seasonal behavior and their appearance of flowing immediately sparked a thrilling hypothesis. Could these be signs of liquid water actively trickling down the Martian slopes in the present day? The implications of such a discovery would be profound. Liquid water is the one non-negotiable ingredient for life as we know it. Finding it actively seeping onto the surface, even temporarily, would completely transform Mars from a dead, frozen world into a potentially habitable one, at least in certain specific locations. The leading theory to explain these streaks involved a special kind of water, not fresh, pure water, which would instantly boil or freeze in Mars's thin atmosphere and sub-zero temperatures, but brine. A brine is water saturated with salts, specifically perchlorate salts, which are known to be abundant in the Martian soil. These salts act as a powerful antifreeze, dramatically lowering the freezing point of water and also slowing its evaporation. Imagine a super salty sludge, so concentrated that it remains liquid at temperatures far below zero. On a warm Martian afternoon, just below the surface, small amounts of ice or water-bearing minerals could potentially release this super saline brine. It would then seep out, darkening the soil as it flows just a little way downslope before evaporating or refreezing, creating the temporary dark streaks we observe from orbit. This water hypothesis was incredibly compelling and placed these RSL sites at the very top of the list for future astrobiological exploration, as they represented the most accessible, potentially wet environments on modern Mars. However, as is often the case in science, the story became more complex with further investigation. As researchers analyzed more data, some puzzling details emerged. Many of the most prominent RSLS were found on slopes that were simply too warm for even super salty brines to remain stable. Furthermore, detailed spectral analysis looking for the chemical fingerprint of water in the light reflected from these streaks consistently came up empty. No signature of water or hydrated salts could be definitively linked to the lineae themselves. This led to the development of an alternative, and in many ways just as fascinating, explanation, the dry flow hypothesis. This theory suggests that the RSLS are not created by liquid water at all, but by the movement of dry, granular material. The process is one of atmospheric mechanics. On Mars, the changing seasons cause significant shifts in atmospheric pressure. As a slope warms in the spring, it can cause small amounts of frozen carbon dioxide, dry ice, trapped just below the surface to sublimate, turning directly from a solid into a gas. This release of gas can destabilize the overlying layer of fine, dust like sand and granules. This destabilization can trigger small avalanches of this dry material. The flowing grains expose darker, underlying soil as they move, creating the dark streak. Then, as the season changes and winds redistribute the brighter dust, the streak slowly fades, only to be reactivated the following year when the cycle repeats. This dry process can perfectly mimic the appearance of a liquid flow without requiring a single drop of water. The debate between the brine seep and dry avalanche models highlights the incredible challenge of remote planetary science. We are trying to solve a complex geological puzzle from hundreds of millions of kilometers away with limited tools. The truth may even be a hybrid of the two. Perhaps some RSLS are dry, while others, in more favorable microclimates, might involve tiny, trace amounts of brine. Regardless of the final explanation, the recurring slope lineae have taught us a crucial lesson about Mars. Its surface is dynamically active today. The planet is not a static, fossilized world, but one that changes with the seasons, its landscapes reshaped by subtle but powerful processes that we are only beginning to understand. They represent a frontier of mystery, a reminder that even on our most studied planetary neighbor, the ground beneath our future rovers' wheels may still hold secrets that challenge our most fundamental assumptions. But if you thought a supernova was the ultimate expression of a star's fury, you haven't yet encountered the true apex predator of stellar cataclysms, a phenomenon so devastating that it makes a supernova look like a firecracker. We are now entering the realm of the gamma-ray burst, the single most energetic explosion known to occur in the universe since the Big Bang itself. To even begin to comprehend the scale, picture our sun, that brilliant, steady furnace that has powered our world for billions of years. Now, imagine it releasing every single joule of energy it will ever produce across its entire 10 billion-year lifespan. That is the total energetic budget of our star. A gamma-ray burst can release that same mind-boggling amount of energy, but it does so not over billions of years, not over millions, not even over a single day. It unleashes it all in a matter of seconds. This is a beam of concentrated destruction so powerful that for a fleeting moment, it can outshine every star in every galaxy in the observable universe combined, focusing the energy of 100 billion suns into a narrow, lethal lance that streaks across the cosmos. These events are not born from the common death of a star, but from the most extreme and rare stellar demises imaginable. There are two primary types, each with its own terrifying origin story. The first, known as a long-duration gamma-ray burst, is thought to be the birth cry of a black hole from the corpse of a hypergiant star, the kind of monster we discussed earlier. But this is no ordinary collapse. For a star to produce a gamma-ray burst, it must be exceptionally massive, low in metals, and crucially, it must be rotating at a ferocious speed. As such a star exhausts its fuel and its iron core collapses, it doesn't just form a black hole, it creates an accretion disk of unbelievable density and temperature. The star's rapid rotation and powerful magnetic fields then channel the energy of the collapse into two narrow jets of plasma and radiation, shooting out from the star's poles at over 99.999% of the speed of light. If you are unfortunate enough to be looking down the barrel of one of these jets, you witness the gamma-ray burst. The second type, a short-duration burst, is an even more violent and compact event, believed to be the result of two ultra-dense stellar corpses, neutron stars, finally spiraling together and merging after a billion-year gravitational dance, or a neutron star falling into a black hole. This collision also forges a newborn black hole surrounded by a fleeting, superheated disk of neutron-rich debris, and once again, powerful jets erupt from the poles, squeezing an almost inconceivable amount of energy into a blast that lasts less than 2 seconds. Now consider the apocalyptic implications for any life that might lie in the path of such a jet. A gamma-ray burst is not an explosion that expands evenly in all directions like a supernova. It is a focused blowtorch, a cosmic sniper rifle. If one were to occur within our galaxy and its jet were pointed directly at Earth, the consequences would be an extinction-level event on a scale we can barely fathom. The first wave would be the gamma rays themselves. Even from a distance of several thousand light-years, this initial blast would deliver a direct, searing flash of high-energy radiation onto our atmosphere. It would not be visible to our eyes, but its effect would be instantaneous and catastrophic. The gamma rays would smash into the upper atmosphere, ripping nitrogen and oxygen molecules apart and catalyzing a chemical chain reaction that would create vast quantities of nitrogen dioxide, a brownish, toxic gas. This would not only paint the sky a sickly, dark color, but it would also initiate the destruction of the ozone layer, the planet's essential shield against the sun's ultraviolet radiation. Within days, our protective ozone layer could be depleted by 50% or more. The immediate aftermath would be bad enough, but the long-term effects would be a slow-moving apocalypse. With the ozone layer shattered, lethal levels of ultraviolet radiation from our own sun would reach the planet's surface, causing severe sunburn in minutes and devastating the base of the planetary food chain, phytoplankton in the oceans. These microscopic organisms are responsible for half of Earth's photosynthesis. Their collapse would trigger a domino effect, starving larger marine life and crippling the entire marine ecosystem. Meanwhile, the nitrogen dioxide haze would act like a nuclear winter shroud, blocking sunlight and plunging the planet into a prolonged period of global cooling and darkness, crippling photosynthesis on land as well and triggering mass crop failures and a global famine. The combination of radiation poisoning, a collapsed food web, and abrupt climate change would likely lead to one of the greatest mass extinctions in Earth's history. There is even speculation that one of the major extinction events in our own planet's deep past, the Ordovician-Silurian extinction around 440 million years ago, could have been triggered by a gamma-ray burst from within our galaxy. The chilling reality is that a nearby gamma-ray burst is a low probability, BUT Chinese letter impact threat. Fortunately, the conditions needed to create them are rare in our modern, metal-rich galaxy, and the likelihood of one being pointed directly at us is extremely small. Astronomers monitor the skies for these events, which occur almost daily in the distant universe, serving as brilliant beacons from the early cosmos. Their incredible luminosity allows us to study the universe's most violent moments and probe the conditions of star formation billions of years in the past. Yet, their existence serves as a humbling and sobering reminder of the raw, indiscriminate power that courses through the cosmos, a power capable of wiping the slate clean across entire galactic sectors in the blink of a cosmic eye, showcasing an environment of energy so extreme that it transcends mere destruction and enters the realm of cosmic sterilization. But what could possibly set the stage for such a grand cosmic arena? A universe vast and structured enough to accommodate everything from colliding neutron stars to silent, wandering rogue planets. To answer that, we must rewind the clock to the very beginning, to a fleeting moment of such profound and violent transformation that it literally shaped everything that followed. In the very first fraction of a second after the Big Bang, the universe underwent a growth spurt of almost inconceivable speed and scale, a period known as cosmic inflation. Picture this, at a time so early that the universe was just 1/1,000,000,000 of a trillionth of a trillionth of a second old, a bizarre form of energy, something akin to a repulsive gravitational force, took hold of the fabric of space-time itself. This energy didn't just cause the universe to expand, it caused it to inflate exponentially, doubling in size not once, but over and over again at a rate far beyond the speed of light. In the span of a mere hundredth of a billionth of a yoctosecond, a timescale so short it has no meaning in human experience. A region of space smaller than a single subatomic particle was stretched to a size larger than our entire observable universe today. This wasn't a gentle unfurling, it was the most violent and pivotal stretch in the history of existence. The theory of inflation elegantly solves several profound puzzles about our cosmos that the standard Big Bang model alone could not explain. The first is the horizon problem. When we look at the cosmic microwave background, the leftover heat from the Big Bang, we see that it is remarkably uniform in temperature in all directions. The problem is, in a universe expanding at a constant rate, there hasn't been enough time since the beginning for light or heat to travel from one side of the observable universe to the other to create this thermal equilibrium. It's as if you walked into a room and found 2 cups of coffee on opposite sides, both at exactly 75 degrees Celsius, but no one had ever been able to travel between them to mix the heat. Inflation fixes this by proposing that the entire observable universe was, in fact, once a tiny, microscopic patch that was in perfect thermal contact with itself before inflation blew it up to a colossal size, preserving that original uniformity. The second puzzle is the flatness problem. Measurements show that the overall geometry of our universe is incredibly flat, meaning parallel lines stay parallel and the angles of a triangle add up to exactly 180 degrees on cosmic scales. For the universe to be this flat after nearly 14 billion years of expansion, its initial conditions would have had to be fine-tuned to an absurdly precise degree at the moment of the Big Bang. Inflation acts like a cosmic iron, stretching any initial curvature in spacetime to such an immense degree that it appears perfectly flat to us, just as the surface of a giant balloon appears flat when you're a tiny ant standing on it. But perhaps the most important legacy of inflation is that it provides the origin story for all structure in the cosmos. According to the theory, the vacuum energy that drove inflation was not perfectly smooth. It was subject to tiny quantum fluctuations, minute ripples in energy that are an inherent part of the quantum world. As the universe inflated at a breathtaking rate, these infinitesimal quantum ripples were stretched to astronomical sizes, frozen into the fabric of spacetime as slight differences in density. These tiny seeds of unevenness were the blueprint for everything to come. After inflation ended, its energy decayed, flooding the universe with the hot plasma of the traditional Big Bang. But the density imprints remained. Over billions of years, gravity got to work, relentlessly pulling more matter toward these slightly denser regions. The tiny overdense spots grew into vast clouds of gas, which collapsed to form the first stars and galaxies. The greatest voids and filaments of the cosmic web itself are simply the negative images of this process, the regions that were slightly less dense and were left behind as matter flowed toward the seeds. So every galaxy, every star, every planet, and every one of us owes our ultimate existence to those microscopic quantum jitters that were magnified to cosmic proportions during that incredible inflationary burst. It was the ultimate act of cosmic amplification, taking the random noise of the quantum vacuum and using it to write the grand design for the universe's most extreme environments. And as our solar system journeys on its 250 million-year orbit around the galactic center, it doesn't sail through a perfect void. We are moving through a diffuse, turbulent ocean of gas and dust known as the interstellar medium, and our sun, in its motion, creates a protective bubble around us, a cosmic force field that defines the very boundary of our stellar neighborhood. This is the heliosphere, a vast, teardrop-shaped region of space dominated by the solar wind. This wind is not made of air, but is a constant, supersonic stream of charged particles, mostly protons and electrons, blasting outward from the sun's million-degree corona in all directions. Think of it not as a gentle breeze, but as a relentless, invisible hurricane of solar plasma, carrying the sun's magnetic field with it as it expands. This outward pressure pushes against the incoming material of the interstellar medium, preventing the vast majority of galactic cosmic rays and other interstellar material from reaching the inner solar system directly. The boundary of this bubble is not a single, simple wall, but a series of complex frontiers. The first major boundary encountered by the solar wind is the termination shock. After racing outward for billions of miles, the wind suddenly slams into the accumulated pressure of the interstellar medium, like a river current hitting a wall. Here, the wind slows down abruptly from supersonic to subsonic speeds, becoming denser and hotter as its energy is converted into heat. Beyond this turbulent region lies the heliosphere's true outer skin, the heliopause. This is the final frontier, the precise boundary where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar wind. It is the very edge of the sun's influence, the cosmic shoreline where the solar system ends and true interstellar space begins. Now, because our solar system is moving rapidly through the galaxy, this entire structure isn't a perfect sphere. It's shaped more like a bullet or a cosmic parachute. The front, or nose, is compressed as we plow forward, while the back stretches out into a long, flowing tail. This motion creates a fascinating and critical structure at the very leading edge, the bow shock. For a long time, astronomers envisioned a dramatic, sharp shockwave preceding the heliosphere, similar to the sonic boom that forms in front of a supersonic jet. The idea was that as the heliosphere moves supersonically through the interstellar medium, it would compress and heat the interstellar gas, creating a standing bow wave of plasma. However, data from NASA, Voyager, and IBEX missions have painted a more nuanced picture. The solar system's speed through the local interstellar cloud, combined with the local magnetic field strength, appears to be just below the threshold needed to form a classic, abrupt bow shock. Instead, the leading edge of our heliosphere is now thought to be more of a bow wave, or a broad, turbulent region of interaction called a bow shock precursor. This doesn't make it any less important. This region is a colossal, million-degree plasma soup where the sun's magnetic field and the galactic magnetic field tangle and interact, a zone of intense particle acceleration and complex physics. It acts as a crucial buffer, further processing and slowing down the interstellar material and cosmic rays before they can even approach the heliopause. The Voyager 1 spacecraft, which crossed the heliopause in 2012, gave us our first in situ measurements from this uncharted territory, confirming that we are indeed inside a protected bubble. The health and size of this heliospheric bubble are not constant. They pulse and breathe with the sun's 11-year activity cycle. During periods of high solar activity, with more frequent solar flares and coronal mass ejections, the solar wind is stronger and more turbulent, inflating the heliosphere and pushing its boundaries farther out, offering our planets even more protection from galactic radiation. During solar minimum, the heliosphere shrinks and weakens, allowing a higher flux of cosmic rays to penetrate deeper into our neighborhood. This dynamic shield is our first and most important line of defense against the harsh galactic environment. Without it, the interstellar medium would press much closer to the orbits of the outer planets, and the background radiation levels throughout the solar system would be significantly higher, potentially altering planetary atmospheres and posing a far greater challenge to the emergence and evolution of life. So, as we float on our pale blue dot, we are not just passive passengers on a rock orbiting a star. We are inhabitants of a dynamic, moving fortress, a cosmic vessel carved out by our sun, sailing through the galaxy within a protective bubble of its own making. Now consider a world where water is not a life-giving liquid but a geological force, its very molecules forced into a crystalline lattice that behaves more like rock than ice. Deep within the vast, churning oceans of water worlds like Gliese 1214b, the immense pressures generated by thousands of miles of overlying water create a realm where the familiar rules of chemistry are rewritten. This is the domain of Ice 7, a high-pressure phase of water ice that exists only under the most crushing forces. On Earth, we know ice as a cold, brittle solid that floats on liquid water. But Ice 7 is fundamentally different in almost every way. It forms at pressures over 2 gigapascals, which is about 20,000 times the atmospheric pressure at Earth sea level, and it can remain stable at extraordinarily high temperatures up to hundreds of degrees Celsius. Unlike the delicate hexagonal crystal structure of common ice you find in your freezer, Ice 7 has a simple, symmetrical cubic lattice. This highly ordered, dense arrangement means that Ice 7 is actually denser than liquid water. This single fact turns our terrestrial experience completely upside down. On Earth, ice floats, a quirk of physics that insulates our lakes and oceans and is crucial for life. But on a massive water world, Ice 7 would not float, it would sink. This creates the possibility of a planet with a layered interior that seems almost paradoxical. A searing hot, liquid water ocean on top, and beneath it, a thick mantle of hot, solid ice. Imagine diving deep into such an alien sea. The water around you would be superheated, kept in a liquid state only by the immense pressure, preventing it from boiling away. As you descend further, the pressure would mount to levels that would crush any submarine. Then you would encounter a boundary, not between liquid and a slushy mix, but between the ocean and a solid floor. Yet this floor would not be made of silicate rock like the seabed on Earth. It would be a seamless, global plain of crystalline Ice 7, a hot ice seabed glowing faintly in the abyssal darkness. The formation of this exotic ice would have profound consequences for the planet's geology and potential for life. A thick mantle of Ice 7 would act as a rigid lid, sealing off the liquid ocean above from the rocky core below. This could prevent the kind of water-rock interactions that, on moons like Europa and Enceladus, are thought to provide the chemical energy and nutrients that could support life. The ocean on such a world might be a vast, sterile body of water, isolated and cut off from the geological engine of the planet. However, the situation may not be so simple. The boundary between the liquid ocean and the solid Ice 7 mantle might not be a perfectly smooth, impermeable barrier. Just as Earth's tectonic plates shift and collide, the Ice 7 layer could experience its own form of geology. The incredible pressures and temperature gradients could cause slow convection within the ice itself, with solid but pliable currents of Ice 7 slowly circulating over millions of years. This solid-state convection could create fractures and faults, allowing tiny amounts of liquid water to percolate downward, or perhaps even enabling cryovolcanism, where plumes of warm water breach the icy crust from below, creating temporary oases of chemical mixing in the deep ocean. The presence of other compounds, like ammonia or salts common in the cosmos, could also lower the melting point of the ice, creating a complex, partially melted boundary layer, a slushy zone of incredible pressure where liquid and this strange, dense ice coexist. The discovery and study of Ice 7 is not just a theoretical exercise. Scientists have actually created it in laboratories using powerful diamond anvil cells, which can squeeze tiny samples of water between the pointed faces of 2 diamonds to simulate the pressures found deep inside planets. These experiments confirm its stability and properties, providing a crucial reality check for our models of exoplanet interiors. When we look out at the growing catalogue of water worlds and super-Earths, we must therefore imagine a far wider range of planetary structures. A planet does not need a silicate mantle to have a solid interior. It can have a mantle of hot, high-pressure ice. This expands the palette of possible planets from merely rocky or gaseous to something entirely new. Aquaplanets with solid ice cores, worlds where the very ground is made of a substance that is both familiar and utterly alien, proving that even something as simple as water can, under the right conditions, become one of the most extreme and foundational materials in the cosmos. Even the most violent impacts in our solar system can have strange and distant consequences, creating chaos far from the point of collision. After the cataclysm that formed Mercury's immense Caloris Basin, a 1,000-mile-wide scar from an asteroid impact so powerful, it nearly shattered the tiny planet. Seismic waves of unimaginable force raced through Mercury's metallic core and solid mantle. These waves did not simply dissipate, they converged. Traveling at thousands of miles per hour, the shock waves focused their energy on the exact opposite point on the planet, the antipode, much like sound waves can concentrate in a specific spot in a cathedral. The result of this planetary focusing is one of the most bizarre and tortured landscapes ever discovered, the chaotic terrain of Mercury. It is a place that looks as though the very ground was picked up, violently shaken, and then dropped back down in a colossal heap. Vast blocks of crust, some spanning dozens of miles across, were jostled and tilted, creating a nightmarish jigsaw puzzle of cliffs and valleys. This jumbled region isn't just cracked, it is fundamentally disorganized, with some mesas standing tall while adjacent blocks have slumped into deep depressions, all interspersed with a confusing network of ridges and grooves. It's a geological snapshot of pure mayhem, a permanent record of the moment when focused planetary vibrations literally rattled the landscape to its core. This phenomenon provides a fascinating window into the internal structure of Mercury. For the seismic waves to have been focused so perfectly, the planet's interior had to be relatively uniform, allowing the shock waves to travel smoothly and reconverge with devastating effect on the far side. If Mercury had a more heterogeneous, layered interior with many pockets of molten or different material, the seismic energy would have been scattered and absorbed, preventing such a dramatic and concentrated upheaval. The existence of the chaotic terrain, therefore, tells us that Mercury's interior, at least at the time of this ancient impact, was consistent enough to act as a planetary lens for seismic energy. This finding aligns perfectly with the iron snow model of Mercury's core, suggesting a largely molten interior that would have transmitted these impact waves with incredible efficiency. When you compare this to our own moon, the difference is stark. The moon has its own giant impact basins like the South Pole Aitken Basin, but you do not find a similarly dramatic chaotic terrain directly opposite any of them. The moon's interior is cooler, more solid, and more fractured, which would have disrupted and dampened the seismic waves long before they could focus on a single antipodal point. Mercury's chaotic terrain is thus a unique signature of its particular internal composition and the sheer, unadulterated violence of its early history. It stands as a stunning example of how a single event can reshape an entire world, creating two completely different, yet intimately connected, extreme environments from one unimaginable blow, a vast, smooth basin on one side and a shattered, chaotic wilderness on the other. But the birth of a star is not a gentle, quiet process. It is a violent and spectacular struggle against its own cradle. Deep within the cold, dark cocoon of a molecular cloud, where gravity is relentlessly pulling gas and dust together to form a new stellar embryo, an opposing force of immense power awakens to push back. This is the dramatic era of the protostar, and its signature is not just the faint glow of contraction, but the brilliant, supersonic scream of its bipolar jets. As the nascent star gathers mass, it doesn't just pull material straight onto its surface. The infalling gas and dust possess too much angular momentum, forcing them to settle into a vast, spinning disk that orbits the protostar, a cosmic carousel of potential planets called a protoplanetary disk. It is from the inner regions of this furious whirlpool that the true stellar fireworks are launched. Intense magnetic fields generated by the churning, ionized gas become wound up like enormous cosmic springs. These fields channel some of the infalling material away from the equator and focus it into two narrow, opposing funnels that erupt from the protostar's poles. What emerges is not a gentle breeze, but a pair of highly collimated jets, blasted outward at speeds that can reach hundreds of kilometers per second, far exceeding the speed of sound in the tenuous interstellar medium. These are not diffuse clouds, they are razor-sharp beams of plasma, cosmic blowtorches that punch through the surrounding dark cloud with surgical precision. The sheer energy involved is staggering. As these supersonic jets slam into the slower-moving gas of the surrounding molecular cloud, they create violent shock waves. The collisions are so energetic that they heat the gas to incandescence, causing it to glow brightly and creating brilliant, compact regions known as Herbig-Haro objects. These are not the jets themselves, but the interstellar smoke from the jet's muzzle flash, the luminous evidence of a celestial cannon firing into the darkness. From our vantage point, we see these objects as beautiful, often symmetrically placed knots of glowing gas on either side of a hidden protostar, their shapes constantly changing over just a few years as new material in the jet rams into older, slower-moving blobs. The scale of these structures is almost beyond human comprehension. A single jet can stretch for several light years across space, a distance so vast it could span the entire gap between our Sun and its nearest stellar neighbor. For a brief period, these jets become the largest coherent structures in their entire galactic neighborhood, a testament to the concentrated power being unleashed by an object that may be smaller than our own solar system. But these spectacular displays are far more than just a celestial light show. They play a fundamental and crucial role in the delicate balance of star formation. A forming star is caught in a gravitational tug of war. Gravity wants to pull everything in, but if it did so unimpeded, the star would spin itself apart due to the conservation of angular momentum. The protoplanetary disk and the bipolar jets are the solution to this problem. The jets act as the system's release valve, carrying away excess angular momentum and rotational energy. By ejecting a small amount of material at tremendously high speeds along the rotation axis, they allow the vast majority of the gas in the disk to slow its spin and continue its journey inward to feed the growing star. In essence, the star has to throw away a little bit of mass in order to gather the rest. Furthermore, these supersonic outflows regulate the final mass of the star itself. The intense radiation and powerful winds from a massive protostar would normally blow away its own gas reservoir, preventing it from growing too large. But for low and medium mass stars like our Sun, the bipolar jets are the primary mechanism that halts accretion. They blast outward in a final, powerful surge, dispersing the remaining gas in the surrounding envelope and effectively cutting off the protostar's food supply. This process ensures that stars do not grow indefinitely but reach a stable size. In a grander sense, these jets are also agents of galactic ecology. As they plow through the molecular cloud, they inject immense energy and turbulence into the surrounding gas. This can compress nearby pockets of gas, triggering the collapse and birth of new stars elsewhere in the cloud, a process known as triggered star formation. Conversely, the jets can also tear apart other potential stellar nurseries, preventing new stars from forming. They are the stellar equivalent of a powerful forest fire, both destroying the old trees and creating the conditions for new growth. So, when we observe the graceful, glowing arcs of a Herbig-Haro object, we are witnessing a critical moment of cosmic feedback. It is the violent, beautiful, and essential process by which a young star asserts its identity, regulates its own growth, and shapes the future of its stellar neighborhood, proving that even in creation, the universe operates through a dynamic balance of immense forces. But to truly understand the beginning, we must tune our instruments not to the brilliant light of stars or galaxies, but to a faint, ghostly static that fills every cubic inch of the cosmos. This is the cosmic microwave background radiation, and it is the most important fossil ever discovered, the cooled and diluted remnant of the universe's ferocious birth. To grasp its significance, we must first rewind the clock to a time before stars, before galaxies, before even atoms could hold themselves together. For the first 380,000 years of its existence, the universe was an opaque, searingly hot plasma, a thick soup of fundamental particles where protons and electrons roamed free, constantly battering into photons of light. In this frenzied environment, light could not travel freely. It would be scattered almost instantly after being emitted, trapped in a perpetual, blinding fog. The universe was quite literally too hot and dense to see through. But then, as the cosmos expanded and cooled, it reached a critical temperature of around 3,000 degrees Kelvin, a threshold that allowed a monumental transformation to occur. The free-flying electrons were finally moving slowly enough to be captured by protons, forming the first stable, neutral hydrogen atoms. This event, known as recombination, was the moment the universe suddenly became transparent. For the first time, the photons that had been trapped in the hot plasma were set free, streaming unimpeded across space. The flash of light from that momentous transition is what we detect today as the cosmic microwave background. It is the oldest light in the universe, a snapshot of the infant cosmos frozen in time when it was a mere 380,000 years old. This radiation did not originate from a single point in space like the light from a distant star. It comes from everywhere at once, from every direction we look. It is the afterglow of the Big Bang itself, a relic of a time when the entire universe was as hot as the surface of a star, and it now fills the vast expanse of space, having been stretched and cooled by the relentless expansion of the cosmos over the ensuing 13.8 billion years. The discovery of this background radiation in 1965 by Arno Penzias and Robert Wilson was a complete accident, but it was the confirmation that cosmologists had been desperately seeking. They were using a large, sensitive radio antenna and found a persistent, inexplicable hiss that seemed to come from every direction in the sky. After meticulously eliminating all possible sources of interference, including famously cleaning out a pair of pigeons and their droppings from the antenna, the signal remained. They had stumbled upon the cooled remnant of the Big Bang, a discovery that earned them the Nobel Prize and solidified the Big Bang theory as the cornerstone of modern cosmology. The most stunning aspect of the cosmic microwave background is its incredible uniformity. No matter where you look in the sky, the temperature of this radiation is almost exactly the same, a remarkably steady 2.725 degrees above absolute zero. This near-perfect sameness presented a major puzzle known as the horizon problem. How could regions of the universe on opposite sides of the sky, which could not have possibly been in contact with each other given the finite speed of light, have reached the exact same temperature? The answer, as we discussed earlier, is cosmic inflation, the incredibly rapid expansion in the universe's first moments, which stretched a tiny, uniform patch to become our entire observable cosmos. Yet, when we look with exquisitely sensitive instruments like the Planck satellite, we find that this uniform background is not perfectly smooth. Imprinted upon it are minuscule fluctuations, tiny variations in temperature of just 1 part in 100,000. These tiny ripples are the cosmic seeds of all structure. They represent the slight over-densities and under-densities in the early universe, the gravitational blueprints that would, over billions of years, pull matter together to form the first stars, the majestic galaxies, the sprawling clusters, and the vast, empty voids of the cosmic web we see today. By meticulously mapping these temperature variations, cosmologists can read the cosmic microwave background like a cosmic barcode, extracting a wealth of information about the fundamental composition and history of our universe. It tells us with stunning precision that the universe is about 70% dark energy, 25% dark matter, and only 5% the ordinary matter that makes up stars, planets, and us. It pins down the age of the universe to 13.8 billion years and confirms the geometry of the cosmos to be flat. This faint, cold whisper of radiation is therefore far more than just an echo of the past. It is the ultimate cosmological tool, a foundational pillar that supports our entire modern understanding of the universe's origin, composition, and ultimate fate. A constant and humbling reminder that the entire vast cosmos we see today grew from the most imperceptible of beginnings. Now, let us turn our attention from the faint cosmic whisper of the microwave background to one of the most visually stunning and dynamically violent structures in our own celestial backyard, the magnificent ring system of Saturn. From a distance, it appears as a serene, golden halo, a perfect disk of exquisite beauty encircling the gas giant. But to view it only as a static piece of cosmic jewelry is to miss the true drama unfolding within. This is not a peaceful, stable belt of ice. It is a frenetic, chaotic arena where the laws of orbital mechanics play out on a scale of unimaginable grandeur, a place of constant creation and destruction governed by gravity's relentless hand. The rings are composed of countless particles ranging in size from tiny, dust-like grains to icy boulders as large as houses, all made almost entirely of water ice. They are not solid, they are a vast, flattened cloud of individual moonlets, each following its own independent orbit around Saturn, and this is the source of the hidden violence. According to Kepler's laws of planetary motion, objects closer to a planet orbit faster than those farther away. This means that every single particle in the rings is moving at a slightly different speed relative to its neighbors. The result is a perpetual, low-gravity demolition derby. Icy particles are constantly rubbing, grinding, and colliding with one another at relative speeds that can be several meters per second. These collisions are not typically catastrophic shattering events, but they are incessant. They act to dampen eccentricities and inclinations, helping to keep the rings remarkably flat and thin, in some places no more than 30 feet thick. Yet within this collisional chaos there is also a countervailing force, aggregation. When collisions are gentle enough, particles can stick together through a weak electrostatic force, a process known as accretion. They can form temporary clumps and elongated aggregates, sometimes whimsically called ring moons or propellers, which are essentially small, embedded moonlets that clear a path in the ring material around them as they orbit. The Cassini spacecraft observed thousands of these propeller features, providing a real-time glimpse into the earliest stages of how moons might form from a disk of debris. But this process of growth is constantly thwarted. Saturn's powerful tidal forces impose a strict limit known as the Roche limit. Inside this critical distance, the planet's gravitational pull on a nearby object is so much stronger on the side facing the planet than on the far side that it overcomes the object's own gravitational binding energy. Any moonlet that grows too large will be torn apart by these differential forces, ripped back into the myriad particles from which it came. The rings exist in this exquisite balance, a celestial dance where gravity simultaneously encourages particles to clump together and then violently shreds them when they become too ambitious. This dynamic equilibrium is most spectacularly illustrated by the role of the shepherd moons. These are small moons that orbit within or just alongside the ring system, and their gravitational influence is like that of a celestial sculptor. A perfect example is the tiny moon Daphnis, which orbits within the 42-kilometer-wide Keeler gap in the ring. As Daphnis travels along its path, its gravity tugs on the ring particles on either side of the gap. It pulls the inner, faster-moving particles forward, slightly accelerating them, while it tugs backward on the outer, slower-moving particles. This shepherding action acts like a gravitational comb, sweeping the gap clear of debris and maintaining its impossibly sharp edges. But the moon's influence doesn't stop there. Daphnis also has a slight orbital inclination, meaning it moves up and down through the ring plane. As it does, it kicks up waves in the ring material at the gap's edges, creating beautiful, undulating ridges that can tower a mile high. A literal mountain range of ice particles, dynamically shaped and then flattened out again by the moon's passing. Other moons, like Prometheus, act as more active and chaotic shepherds. This potato-shaped moon has an elliptical orbit that brings it periodically very close to the inner edge of the F-ring. Each time it swings by, its gravity plunges into the ring like a cosmic hand, dragging out long, dark channels and creating intricate braids and kinks in the ring's structure. It steals material from the ring, pulling it into temporary streamers before its motion carries it away, leaving the ring to settle until the next gravitational encounter. This continuous gravitational pandemonium prevents the F-ring from spreading out and diffusing, confining it into a narrow, bright band that is one of the most active and ever-changing places in the entire Saturnian system. The rings are not a permanent feature. The very collisions that define them also sap their energy, causing the ring particles to slowly spiral inward toward Saturn. Combined with erosion from micrometeoroid bombardment and the effects of solar radiation, this means the brilliant rings we see today are likely a transient spectacle in the solar system's history. They may be the shattered remains of a former icy moon that ventured too close to Saturn's Roche limit and was torn asunder, or the leftover debris from a colossal collision between moons billions of years ago. However they formed, their current existence is a fleeting, dynamic ballet, a breathtakingly beautiful system that is simultaneously being sculpted by shepherd moons, ground down by collisions, and slowly draining away into the planet itself. They are a masterclass in orbital dynamics, a place where we can witness the fundamental processes of planet formation and destruction playing out in real time, proving that even the most serene-looking objects in the cosmos can harbor a world of hidden, beautiful violence. But if you thought Saturn's rings were the only strange feature in its extensive family of moons, you haven't yet met Hyperion, a celestial body that looks less like a world and more like a piece of cosmic coral or a pumice stone that has been blown up to a planetary scale. Orbiting the ringed giant is this incredible, spongy moon, a world so bizarre that its very structure defies our conventional understanding of what a solid object should be. When the Cassini spacecraft first captured close-up images of Hyperion, scientists were met with a landscape unlike any other in the solar system. It is not pockmarked with simple impact craters. Its entire surface is a chaotic, porous matrix of deep, dark pits with sharp, jagged ridges forming a fragile-looking honeycomb of rock and ice. This isn't a surface you could easily walk on. It's a delicate, crumbling lattice, a celestial skeleton where over 40% of the interior is empty space. The secret to this incredible porosity lies in Hyperion's exceptionally low density. Measurements show that this 270-kilometer-wide moon has a density only slightly more than half that of water. This means if you could find an ocean large enough to place it in, Hyperion would not just float, it would bob like a colossal, waterlogged sponge. This profound lack of solid substance points to a fascinating internal history. Hyperion is likely not a monolithic chunk of rock and ice that formed in one piece. Instead, it is almost certainly a rubble pile moon, a loose collection of icy fragments that were gravitationally gathered together in the distant past, following a catastrophic collision that shattered a larger progenitor body. The fragments never fully compacted under their own weak gravity, leaving vast gaps and caverns throughout its interior, creating a world that is more a pile of icy boulders held together by a gentle mutual attraction than a single cohesive sphere. This fragile structure has profound consequences for its appearance and its interaction with the space environment. Hyperion's incredibly weak surface gravity, which is only about 1 or 2% of Earth's moon's pull, means that nothing ever truly settles. When an impactor, a small asteroid or comet, strikes this spongy surface, it doesn't create a traditional crater with a raised rim and ejected debris field. Instead, the impactor essentially just punches a hole, compressing the fragile, porous material inward. The ejected material isn't thrown high into the sky. Most of it simply vanishes, falling back into the countless voids and cavities that riddle the moon's interior, or it is lost to space entirely because the escape velocity is so minuscule. This process, repeated over billions of years, has carved out the deeply sunken, cavernous pits that give Hyperion its signature look, with crater walls that are incredibly dark. And this darkness presents another layer to the mystery. The floors of these deep craters are coated with a layer of reddish-black gunk, a material that spectral analysis suggests is rich in complex hydrocarbons. These are long chains of carbon and hydrogen atoms, the very building blocks of the more complex organic molecules necessary for life. In the deep cold traps of these craters, which are in permanent shadow and among the coldest places in the solar system, these hydrocarbons have been preserved for eons, possibly delivered by impacting comets or formed in place through the interaction of solar ultraviolet radiation with ices on the surface. This dark material, clinging to the lowest points of this bizarre sponge world, makes Hyperion a kind of natural laboratory for probiotic chemistry, a place where the universe's raw ingredients for life are being stored and mixed in the deep freeze. The Moon's chaotic rotation adds one final touch of strangeness to this already alien portrait. Unlike our own Moon, which is tidally locked and shows us only one face, Hyperion tumbles through its orbit in a completely unpredictable, chaotic spin. Its rotation is not regular. Its axis wobbles so much that there is no way to predict which part of its surface will be facing Saturn from one orbit to the next. This erratic behavior is a direct result of its irregular shape and its orbital resonance with the much larger moon Titan. As the two moons pass each other, Titan's immense gravity gives Hyperion a periodic, irregular gravitational kick, preventing it from ever settling into a stable, synchronous rotation. This means there is no permanent day side or night side. The sun rises and sets at random intervals across that pitted, sponge-like landscape, creating an utterly disorienting and ever-changing pattern of light and shadow that dances across the deep, hydrocarbon-filled pits. So Hyperion stands as a unique monument to fragility and chance. It is a world that is mostly empty space, a collection of icy fragments barely holding on to one another, its surface sculpted not by conventional geology, but by impacts that simply sink into its porous body, preserving in its darkest recesses the complex carbon chemistry that is the precursor to life itself. It is a testament to the fact that in the cosmos, even something as seemingly simple as a moon can be a complex, chaotic, and wonderfully strange individual. After exploring the fragile, spongy terrain of Hyperion, we arrive at our final destination, a realm that exists not in our telescopes, but in the elegant equations of theoretical physics. To complete our journey through the universe's most extreme environments, we must confront a concept that stretches the very fabric of reality and challenges our understanding of cause and effect, the white hole. If a black hole is a cosmic one-way street, a gravitational pit from which nothing, not even light, can escape, then a white hole is its theoretical opposite, a celestial gusher, a point in space where matter and energy can only pour out and nothing can ever enter. The idea emerges directly from the mathematics of Einstein's theory of general relativity. The solutions to his field equations that describe a black hole are, in a purely mathematical sense, time-symmetric. This means if you were to take the equations for a black hole and reverse the direction of time, you would get the description for a white hole. It would be like running a film of a black hole in reverse. Instead of matter vanishing forever behind an event horizon, it would be a point from which matter and radiation erupt into the universe in a continuous, unstoppable fountain. Imagine a singularity similar to the one at the heart of a black hole, but instead of pulling everything in, it violently expels everything. The event horizon of a white hole would be an impassable boundary in the opposite sense. You could see the light and matter blasting out from within, but you could never cross the threshold to get inside. Any object or light ray approaching a white hole would be repelled, as if the very geometry of space-time around it was pushing outward with irresistible force. While this makes for a fascinating thought experiment, the physical plausibility of white holes is a major point of debate. For a white hole to form, you would need a region of space-time that, from the very beginning of the universe, was set up to explode outward in this specific, mathematically pristine way. It couldn't form from the collapse of a star as a black hole does. Some theorists have proposed that a white hole could be the other end of a black hole, connected by a space-time tunnel known as an Einstein-Rosen bridge or a wormhole. In this scenario, matter falling into a black hole in our region of the universe could be spewed out from a white hole in another time or place, a concept that has fueled countless science fiction stories. However, this idea runs into significant physical problems. The intense gravitational forces and the instability of such wormholes, according to our current understanding, would likely collapse them instantly, preventing any such travel. Furthermore, white holes seem to violate the second law of thermodynamics, which governs the increase of disorder or entropy in the universe. A black hole has incredibly high entropy, which fits neatly into our thermodynamic understanding of the cosmos. A white hole constantly emitting energy without ever absorbing any would appear to be a device for decreasing entropy, which is not something we observe happening naturally. This has led many physicists to conclude that while white holes are beautiful mathematical curiosities, they are probably not real, stable objects in our universe. They represent a potential pathway that the laws of physics simply do not allow to be taken. Yet, the concept continues to captivate cosmologists because it pushes our models to their absolute limits. Some of the most intriguing modern speculation links white holes to the very origin of the cosmos itself. One compelling, though highly speculative, hypothesis suggests that the Big Bang itself could be viewed as a white hole event, a primordial singularity from which all the matter and energy of our universe erupted. This offers a novel perspective on creation, not as an explosion in a pre-existing space, but as the spontaneous appearance of spacetime from a white hole singularity. Another fascinating connection lies in the field of quantum gravity, where scientists attempt to reconcile general relativity with quantum mechanics. In loop quantum gravity, for instance, there are models suggesting that the immense gravitational collapse that forms a black hole could eventually rebound due to quantum pressure, causing the black hole to transform into a white hole, effectively re-emitting all the information and matter it had consumed over an almost unimaginably long period. While we have no observational evidence for such an event, it offers a potential solution to the infamous black hole information paradox, a deep puzzle about whether information is truly lost inside a black hole. The true value of the white hole concept, therefore, may not be in discovering one with our telescopes, but in how it forces us to think. It compels us to question the arrow of time, the ultimate fate of matter, and the very boundaries of what is physically possible. It represents the ultimate cosmic extreme, an environment defined not by crushing pressure or searing heat, but by the fundamental reversal of physics as we know it. As we conclude our count of 50 facts, the white hole stands as a powerful symbol of the universe's deepest mysteries, reminding us that the most profound frontiers are not always those we can see, but those we can only, for now, imagine. And so we reach our final destination, a place not found on any star chart, but one that exists within the elegant, twisted logic of mathematics itself. We've navigated worlds of fire and ice, witnessed stellar collisions and cosmic voids, but to conclude our countdown, we must confront the ultimate theoretical extreme, the white hole. If a black hole is a cosmic drain, a one-way street where matter and light vanish forever, then a white hole is its bizarre, hypothetical mirror image, a celestial fire hydrant, a point in space-time where energy and matter can only erupt outward and from which nothing can ever enter. The concept doesn't come from wild speculation, but directly from the cold, hard beauty of Einstein's field equations for general relativity. These equations, which describe how mass and energy warp the fabric of space-time, are, in a purely mathematical sense, time-symmetric. This means if you take the precise solution that describes a black hole, a Schwarzschild metric, and simply reverse the direction of time in the equation, the result describes a white hole. It's like watching a film of a star collapsing into a black hole, but then running that film backward. Instead of an implosion, you see an explosion. Instead of an event horizon that only allows entry, you get a boundary that only permits exit. Imagine a singularity similar to the infinitely dense point at a black hole's heart, but instead of pulling everything in, it perpetually and violently expels everything. Its event horizon would be an impassable wall of repulsion. You could observe the brilliant light and matter gushing out from within, but any attempt to approach it would be thwarted. The very geometry of space-time around it would push you away with an irresistible force, as if you were trying to swim up the business end of a cosmic geyser. This mathematical elegance, however, slams directly into the harsh realities of physics as we understand them. The most significant collision is with the second law of thermodynamics, one of the most sacred principles in all of science. This law states that the total entropy or disorder in a closed system like our universe can only increase or remain the same over time. It can never spontaneously decrease. A black hole fits beautifully into this framework. It is an object of immense entropy, a cosmic graveyard that swallows order and radiates a tiny amount of heat, perfectly consistent with thermodynamic law. A white hole, however, behaves like a thermodynamic rebel. It would be a source of energy and order, constantly spewing out low entropy matter and radiation without ever taking anything in. This would effectively create a machine that decreases the overall entropy of the universe, a process that is as fundamentally forbidden as a river spontaneously flowing uphill. For this reason alone, most physicists consider stable, permanent white holes to be physically impossible in our universe. They represent a potential pathway that the laws of nature simply do not allow to be taken. Beyond thermodynamics, there's the profound problem of formation. We have a very clear and observed mechanism for how black holes form, the gravitational collapse of a massive star's core. But how would a white hole ever come into being? It couldn't form from collapse. Its very definition requires it to have been exploding outward from the very beginning. Some have theorized that a white hole could be the other end of a black hole, connected by a hypothetical tunnel through space-time known as a wormhole. In this science fiction-friendly scenario, matter falling into a black hole here could be spewed out of a white hole somewhere else, perhaps in a different time or even a different universe. Yet, this enticing idea is plagued with instability. The immense gravitational forces and the influence of any stray particle of matter would likely cause such a wormhole to snap shut instantaneously, collapsing into a singularity long before anything could traverse it. This inherent fragility makes traversable wormholes, and by extension their connected white holes, exceedingly unlikely. So why does the concept persist, captivating cosmologists and theoretical physicists? Its true value lies not in its plausibility as a real object, but in its power as a theoretical tool that pushes our understanding to the absolute brink. It forces us to ask profound questions about the arrow of time, the origin of the cosmos, and the ultimate fate of information. One of the most intriguing modern speculations comes from the quest to unite general relativity with quantum mechanics, a theory of quantum gravity. In frameworks like loop quantum gravity, there are models suggesting that the immense gravitational collapse of a black hole might not be the final word. Instead of forming a permanent singularity, quantum gravitational effects could create a tremendous repulsive force, causing the collapse to rebound. In this model, after a phenomenally long time, a black hole could potentially transform into a white hole, re-emitting all the matter and information it had once consumed. This offers a potential, though highly speculative, solution to the infamous black hole information paradox, which puzzles over whether information is truly lost forever inside a black hole. On an even grander scale, some have dared to propose that the single most extreme event we know of, the Big Bang, could itself be viewed as a white hole event. Our entire observable universe, in this mind-bending perspective, would be the interior of a primordial white hole, with the initial singularity representing the moment it began its explosive outward expansion. This reframes the creation of everything not as an explosion in space, but as the very eruption of space-time from a white hole singularity. While we possess no observational evidence to support this, it demonstrates how the white hole concept compels us to rethink our most fundamental assumptions. And so, as our journey through 50 facts about the universe's most extreme environments concludes, the white hole stands as the perfect final frontier. It is an environment defined not by crushing pressure, lethal radiation, or unimaginable cold, but by the sheer extremity of its theoretical paradoxes. It is a place that likely does not and cannot exist, and yet by merely contemplating it, we are led to the very boundaries of physics, to the edge of what is knowable. It is a brilliant, impossible dream in the equations of relativity, a ghost in the cosmic machine that reminds us that the universe's greatest wonders are not only those we can see, but also those we can, for now, only imagine. And so, from the theoretical fire hydrant of a white hole, our journey through 50 of the universe's most extreme environments comes to a close. What an astonishing voyage it has been. We have stood on the shores of methane lakes under an orange, hazy sky, felt the phantom sting of a horizontal blizzard of molten glass, and peered into the abyssal heart of a black hole where time itself grinds to a halt. We have witnessed planets where it rains diamonds, stars that spin hundreds of times a second, and voids so empty they echo with the silence of billions of missing galaxies. This tour has revealed a cosmos that is not a serene and peaceful void, but a dynamic, chaotic, and often violent arena, a place where the laws of physics are stretched, tested, and rewritten in environments of unimaginable pressure, temperature, and scale. From the crushing gravity of a neutron star to the searing inferno of a lava world, from the silent, dark wanderings of rogue planets to the brilliant, galaxy-quenching fury of a quasar, the universe showcases a diversity of existence that truly dwarfs our wildest science fiction. This exploration is far more than just a catalogue of celestial curiosities. It is a fundamental pursuit of understanding. By studying these cosmic extremes, we are not merely satisfying our curiosity. We are running natural experiments on a grand scale, testing the very bedrock of physics under conditions we could never hope to recreate in a laboratory on Earth. The intense magnetic field of a magnetar teaches us about the limits of electromagnetic force. The warped space-time around a black hole confirms the predictions of general relativity with stunning precision. The chaotic dance of particles in a supernova remnant shows us how the very atoms that make up our bodies were forged in stellar furnaces. Each of these hostile, alien environments is a natural laboratory, offering us a unique window into the fundamental rules that govern everything, from the smallest subatomic particle to the largest structures in the cosmic web. In doing so, this journey holds up a profound mirror to our own place in the cosmos. We live on a world of incredible, delicate balance, a fragile oasis of moderate temperatures, liquid water, and a protective atmosphere. Confronting the sheer violence and hostility of the broader universe, from the sterilizing radiation of gamma-ray bursts to the crushing pressures of water worlds, makes our own blue marble seem all the more rare, precious, and beautiful. It highlights that we are not the center of the universe, but we are a part of something infinitely vast, complex, and magnificent. Our drive to understand these extremes, to push the boundaries of our knowledge out to the very edges of reality, is one of the most defining and noble traits of humanity. It connects us to the cosmos not as separate observers, but as conscious matter born from stardust, now striving to comprehend its own origins. So, as we conclude this epic countdown, we want to hear from you. Which of these 50 extremes captured your imagination the most? Was it the eternal diamond hailstorms within the ice giants, the lonely, sunless journey of a rogue planet through the galactic void, or the mind-bending time dilation at the edge of a black hole? Let us know in the comments below which environment you found the most fascinating, terrifying, or awe-inspiring. If you enjoyed this deep dive into the raw power and wonder of the cosmos, please subscribe to the channel for more voyages to the frontiers of knowledge. The universe is filled with mysteries waiting to be uncovered, and we are just getting started. Thank you for joining us on